in quantum condensed matter, quantum dynamics, and things like that. And today he'll tell us about emulating strong correlations using ultra-cold atoms.
Sugar? Okay, so I would like to begin by thanking the organizers for inviting me here in this conference, and it has been a nice conference so far. So, okay, so the topic of the talk today would be emulating strong correlations and dynamics using ultra-cold atoms. So, but before that, so we are sort of celebrating 100 years of quantum mechanics, and the thing that I would like to sort of say, just one line regarding that, is that although historically it's taught and understood in a slightly different way, quantum mechanics is not just the science of the micro world, it's also the science of the macro world. And one of the simplest way of understanding this, which we sort of come across in our daily life all the time, is basically if you take a piece of wood like this and a piece of copper, and just measure their electrical resistance, and you would see that it's the order of magnitude difference between these two. If you take the ratio, that's a fantastic number of the order of 10 to the power, I think 15 or 16 or some such stuff. Okay, and there is no classical theory which can give you this order of magnitude, and quantum mechanics is the only known theory which can successfully predict this. So and of course we know about superconductivity and that kind of stuff, and so quantum mechanics also takes care of the macroscopic world, and that's a very essential point. But let me come back to the main subject of the talk, and that's emulating strong correlations using ultra-cold atoms. And here is so here is the outline of the talk. So first I'm going to talk a bit about this ultra-cold atoms and emulating strong correlation using it, and the paradigmatic Bose-Hubbard model, and that would be the basic features. That's the part one of the talk. Then I'm going to talk in a little more details about emulating strong correlations, and I'm going to talk about what happens when you tilt this lattice, that is apply a quote-unquote electric field, and I'm going to explain what it means. And also another platform which has gained prominence over the recent years, that's Rydberg chain and arrays. And then I'm going to go to part 3, where I'm going to show how this kind of platforms can host non-equilibrium dynamics. So a brief introduction to what we call as eigenstate thermalization hypothesis and its violation. I'm going to only talk about one possible weak violation of this eigenstate thermalization hypothesis, that is due to presence of these quantum scars. And the reason for this is that this quantum scars is seen in this Rydberg atom platforms, which was introduced earlier. And this will most likely exhaust my time, and if I have time, I'm going to go to this part 4, which is this Rydberg ladders, which is a fascinating system, but I'm not entirely sure if I would get there. Okay, so let's start with part 1. So this is about ultra-cold atoms and emulating strong correlation using light. So when we say about ultra-cold, cold has a human definition, right? What appears to be cold in Madras and what appears to be cold in Greenland are two very different things. But when it comes to science, we talk about in terms we go beyond this human perception of cold and other things, and we talk about temperatures such as liquid nitrogen and liquid helium temperatures, which is roughly like 77 Kelvin and 4 Kelvin, and which is pretty, close to absolute zero. But in these cold atoms, people have taken it to a whole new level, and using this laser cooling and evaporative cooling, which Umakant talked about in the last yesterday, they could get into temperatures which is in orders of tens of picokelvins. And I believe the current record is 38 picokelvin, which is basically realized in some German group in Bremen. The perspective about how cold these atoms really are, well, that's the coldest known place in the universe, because even outer space is like microwave radiation temperature, which is way hotter than this. The question that comes is that how do you measure such temperature? I mean, you just can't stick a thermometer in there because it's going to just simply heat up everything. So what you do is that you take a bunch of these bosonic atoms, and at this temperature, almost everything, and people typically take rubidium atoms, which is a well-known platform. They form a BEC, a Bose-Einstein condensate. And if this temperature was really absolute zero, this central peak, which tells you how many bosons are there in the K equal to 0 or the Bose-Einstein condensate state, that would be a delta function, 0 width. And really it's the width of this peak which gives you a measurement about how strong the interaction effects are and how strong the temperature, thermal fluctuations are. And from that, people can do calculation and get an idea about how cold one got. Okay, so that's another. So the interesting part about it is that that's one way of measuring temperature which you normally don't think about. So, So let's just see, how you do this cooling. Umakant has already talked about this in the last day, but I'm just going to go through this very quickly. One of the cooling techniques that Umakant and many others use is this Doppler cooling of atoms. So what you do is that you create these atoms, they are cooled down to about a few Kelvin temperature, as Umakant showed in the last this thing, and you apply these lasers, which are slightly detuned from the resonance frequency of the lasers. So you see, when an atom encounters light, it reacts with this only if the frequency of the light matches the resonance frequency of the atoms. Otherwise, it just lets it pass. Okay. However, if you now detune it such that when an atom moves towards this bunch of these photons, due to Doppler effect, it sees a resonance frequency. Then the atoms are going to preferentially scatter from these photons only when they are moving towards it. Okay. And it's not going to scatter if it's moving away or if it's moving in the same direction. So once that happens, so the atom and the photon, so there is this, so the atom after absorbing this light goes into the excited state, and after some time it just emits this radiation back and comes to the ground state. However, the point is that this radiation is of course emitted randomly in any arbitrary direction. However, the momentum transfer happens only in one specific direction. And therefore, over many such scattering processes, there is a net decrease of momentum because the atom dumps its momentum to the photon, and therefore its momentum or velocity and therefore effectively average energy and temperature decreases, and this is how optical molasses are created. And this process can take you up to a microkelvin of temperature.
How long does it take?
Sorry?
How fast is the process?
Oh, that I don't know. It's not sure. Oh, no, much faster than seconds. No. I mean, but I'm not entirely sure whether it's microseconds or even faster than that. I mean, there is a transition rate. I don't have the number on the top of my head. Sorry.
Other than rubidium, any other thing which is?
Yeah, there are a lot of those atoms actually. I think there is this, people work with potassium, calcium, sodium, many kinds of different atoms. But rubidium apparently is preferred because of several properties which I'm going to come in a moment. Okay. Width of the peak, I'm going to come to that. You measure the momentum distribution, and there is a way of doing that. I'm going to just come to that. Just give me 1 minute. And after this, after you have created this optical molasses, what happens is that you cool it further by something known as evaporative cooling. I mean, Umakant has already told you about this. So what you do is you lower this magnetic trap slowly so that the atoms at the top, which is also the most energetic atoms, just escapes the trap. So you lose atoms, but you decrease the temperature and also increase the phase space density, which Umakant was talking about in the last this thing. So essentially, this can take you to order nanokelvin temperatures, very easily. And by the way, this is called evaporative cooling because this is exactly how your coffee cup gets cold in a winter morning. Atoms simply escape from the surface. This is exactly what happens. So, and then so suppose now you have done this, you have achieved this nanokelvin temperature and you have got your BEC. And then to emulate strong correlation, you need something else. So what you do is that you apply so you have this BEC out here, and you apply counter-propagating lasers, which forms a standing wave of light. Now these atoms have a polarizability, and therefore for sufficiently detuned laser frequency where there is no direct absorption, it feels a potential which is proportional to this polarizability of the atom alpha times mod E square. And if you tune this frequency right, this alpha can be a positive number, so that the atoms feels a potential which is minus alpha E squared. It just wants to sit in the bottom of this standing potential. But this is not very different from what we see in condensed matter, because there is also this individual sites over which electrons are localized and stuff like that, and there is this periodic pattern. So this allows you to create block theory for bosons using light. Okay, so that's the main point about this thing. And when you make the lattice deep enough, as we'll see, the atoms go from a superfluid state to an insulating state, and that's how strong correlation is emulated in these models. So, yeah. Yes, one can make a three-dimensional lattice. So in fact, nowadays you can do any dimensions, 3, 2, 1, whatever. So here is the first experiment which sort of got this field into some prominence about this strong correlation. So this was done in Emmanuel Bloch's group. It was in 2001, and what they did is that they took this BEC and then they ramped up the potential depth, okay, up to some V naught, which is also Vmax here, okay, and then they let the atoms stay there for about 20 milliseconds. Okay, so the ramping time is roughly 80 milliseconds, and then they let these atoms stay there for 20 milliseconds, and then what they do is a very interesting measuring technique. They drop the trap, the lattice, and everything, and let these atoms just fly apart. So because it's a free flight, modular interaction effects which are weak in this case, because it's a free flight, if you see these atoms fly and hit a screen, the position of the atoms on the screen is determined only by its initial velocity. Okay, because it just flies, right? So, and it's really the initial velocity that you will see, and therefore the position distribution of these atoms on the screen is the velocity distribution of the atoms inside the trap, and this is the way you measure momentum distribution of atom. And this is exactly how you measure the width of this central peak, to answer your question. Okay. I'm sorry?
It's a special width.
Special?
The width is the special width, not the width of the probability.
This width apparently is the momentum distribution width of the bosons.
No, along the space text, because you said it comes from here, and because it's a flight, this ring will be coming, the spread which is determined by this.
But you see, which direction it will fly depends on the initial velocity.
That's what I mean. Yeah.
So this width essentially measures the velocity distribution of the atom inside the trap. Imagine that the atoms...
I understand.
Yeah. So the position distribution on the screen is the velocity distribution inside the trap, or momentum distribution if you want to. Yeah.
Okay.
Yes, this is a destructive measurement. Once you do this, you destroy the system. No, not here. No, not here. This is just a strict. Sorry? Why would you do that? No, I mean, sorry, I didn't understand the question, probably.
So if you detune and then things that are, like maybe absorbed, which are moving towards...
No, but you see, the point is that you want to measure the momentum distribution of all the bosons which are in the trap to get a distribution. And this is the simplest way of doing it. So the Doppler shift is not going to work probably because many bosons have many velocities and there is no single Doppler shift which is... iffy. Maybe we can talk after, yeah. So, yeah, sure.
How many lattice sites are
there typically in a trap?
This depends. I mean, for a 3D trap like this, there are about 10 to the power 6, something of that order. Okay. This really depends on experiments and what you do with this kind of things.
So you really have like a million?
Yes, Yes, for this 3D experiment you have order 10 to the power 6, I think, if I remember correctly. Okay. So what happens is that when this trap essentially is really close to 0 or small, you find that the bosons are very well localized around k equal to 0. So that's the central peak. And if you have a lattice, there are these sub peaks which occurs because of translational symmetry. But then something interesting happens. Once the trap is really large, you see that this central peak disappears, and all you have is a blob. Now, what does this blob mean? It means that the bosons are distributed among all possible momenta inside the trap, and by uncertainty principle, that means that they are very well localized inside the trap. Okay? So this apparently is showing you a localization to delocalization transition in momentum space. This thing out here is an insulator, everything is localized. This thing here is a superfluid, everything is at k equal to 0. And this thing out here where the central peak disappears apparently is taken to be the position of a superfluid insulator transition. And this is one of the cleanest realization of a quantum phase transition, because temperature out here is at least 2 orders of magnitude lower than all other scales in the problem. Okay, so this is really quantum. This part is the BEC condensate. This part is our bosons, but they are insulating, and they are Mott insulators, which is insulating state. And I'm going to talk a bit about the theory of this in a moment. Okay. So here are some nice pictures. This is how the bosons hit the trap, and this is how the peaks look. So this is the Mott insulating state where there is no central peak, and this is where you are still in the superfluid state, and that kind of stuff. These are momentum distributions. These are constructed from positions of the bosons on the screen, which tells you about the momentum inside the trap. Okay, so how do we model this? How do we understand this? So apparently what happens is that, in here the energy scales are such that you can describe this model by a single band model where these bosons can hop from one side to another, and the interaction between them can be approximated because they are reasonably local. These are not charged bosons. So you can sort of approximate them by an on-site interaction. Okay, and the reason you can do this is that the other bands, the single particle bands of these bosons inside this well, is way higher than either U or this hopping strength T, and therefore you can neglect those. There is very little interband transition, and therefore it's a single band physics, and you basically just look into this. Okay. So we are going to study this model a little bit to understand the transition. Now, yeah, sorry, what is it? N is B dagger B. It's the density operator on a given site. Okay, so how do you do this preliminary analysis? And this is particularly simple because the Mott state is pretty simple out here. So what happens is that if I go into a really large lattice depth where the hopping, which is exponentially suppressed with the lattice depth, goes to 0, then I have only this on-site term, and I can find out if I have 1 particle per site, if I have 2 particles per site, 3 particles per site, what are the energies. And this analysis is really simple, and it tells you that when your chemical potential out here lies between 0 and U, you have a state with 1 boson per site. And then the next question you would ask is that suppose now I lower my lattice depth a bit and I allow these bosons to hop, does this state with 1 boson per site, the Mott state where everything is localized, immediately disintegrates? Or is there a stability to this phase? How do you see this? Well, the easiest way to see this is that one adds either a particle or a hole on top of this Mott state. Now, if I do that, I'm going to have an energy cost of U minus mu if I add a particle, because it's going to cost an energy U, and you are going to gain an energy mu. Okay, but now you see that this boson can keep on hopping from site to site. It doesn't cost an extra energy if it does, and this is a simple hopping problem, and one can show that the energy lowering because of this hopping is equal to 2 times z being the coordination number of the lattice. So if it's a square lattice in 3D, it's just 6, it's 2D, it's 4, the number of nearest neighbor site of the lattice, okay, times the hopping amplitude. And you see that this excitation energy becomes negative or goes to 0 at a critical value of this hopping, which is u minus mu by 2 times z. Okay. Now, if you increase t further, what it means is that your excitation energy becomes negative, which in perturbation theory is a nonsensical answer. But what that nonsensical answer is telling you is that the ground state from which you have started from is not the ground state of the system anymore. And that's why your perturbation theory is not working. And therefore, this is a signature of destabilization of the ground state. And so you get a critical hopping for adding a particle, you get a critical hopping for removing a particle, and these two are different because Boas-Savart model is not a particle symmetric system. Adding a particle and removing a particle is not quite the same. And this is a signature of the destabilization of the Mott phase, which importantly happens at finite value of this critical hopping. So, so you can go beyond this simple picture, and people have studied this quite a lot. So apparently what you can do is, you can do higher order virtual process corrections to this process, to this, this quasi-particle addition and removal process. That's done by Friedrichs and Monian in the initial paper. You could do a mean field theory, which was first done by Fischer at 89, and then Tivier wrote a very interesting paper on this in 93 or 92, something like that. And then there is this quantum Monte Carlo studies on 2D systems by Nandini and Kraut, and all of them established a phase diagram. Okay, so you have a hopping on one axis and the chemical potential on the other, and this is your, sort of the phase diagram from mean field theory, and then if you include fluctuation, that's the phase diagram, and so on. The Monte Carlo is somewhere. Yes, of course. Yeah. No, this is bosons. It's Monte Carlo can be done without any sign problem.
But when chemical potential is added, then also
No, it's bosons, so no signs. Yeah. Single component bosons, single component bosons in a standard lattice, even with finite chemical potential, no
it's
problem.
not complex.
No. Well, this is the boson hopping. Sorry, I'm switching. This is just T that we had. The hopping strength from one lattice site to the next. That's in units of U. So the point is that all these things, of course, do a lot, but they don't give you much information about the nature of the Mott state. You see, far away from the transition, of course, this Mott state is a featureless state with one particle per side, but near the transition, the character of this Mott state also changes. And okay. So for that, essentially we worked on this long time back. I mean, we tried to analyze this Mott phase using a Green's function approach, and here it's a strong coupling Green's function approach. I don't want to get into the details of this, but the point is that it allows you to calculate the momentum distribution of these bosons even in the Mott phase, not only in the superfluid phase, and that's what this method achieves. And apparently what you see is that as you move towards this transition, there is a precursor peak which happens at k equal to 0. So it's like the system knows, it's approaching this transition and it will get into this superfluid phase. So you have this peak, and thankfully some experimentalists took this seriously, and later, they did this measurement and tried to fit our theory using this. And apparently the match is not too bad, given that there is only one single fitting parameter, which is the chemical potential. Okay. So this is what I wanted to say about the Boas-Savart model and how we understand the transition, the superfluid insulator transition in this kind of systems. And I must say that there are a lot of analytical and numerical works has been done on this model, and people have sort of approached this from different angles. They have tried to add, one important thing is what happens when you add disorder to the system, which you can do by adding a spectral laser, which makes the height of this optical lattice random. There is a random component to that. And as a result, what happens is that these effective parameters, T, U, etc., they can become random. There is a random component to those. And in those kind of system, people have tried to look for Bose glasses, whether you can have a glassy phase or not, with strong randomness and stuff. And there are many other works. And also another important in this system, which I haven't touched upon, is to take seriously the trap, which changes this physics quite a bit. It makes the density distribution uneven. It gives it a so-called wedding cake structure, in the sense that the density is largest at the center, and then it's a little bit smaller towards the edge, and so on and so forth. But those are all well understood, and all these complications now is understood both theoretically and experimentally, to the best of my knowledge. But then I'm going to talk a little bit about this other aspects of this emulation of strong correlation. So what happened is that after people understood that this Bose-Hubbard model can be done and this kind of strong correlation physics can be emulated in these platforms, people wanted to see whether one can sort of get to the next level where you get a state which breaks translational symmetry and is strongly correlated. Okay, so that was there. And one of the possible thing of that people looked into is basically realization of 2 or more species of ultra-cold atoms. Okay, and this is also studied in using several means. And the point is that there is an antiferromagnetic phase here, which where by antiferromagnetic phase I mean that atoms of species 1 occupy one sublattice and the atom of species 2 occupies the other sublattice. And there are lots of these interesting phases. That's of course one way of doing it. The other way of doing it is to add a nearest neighbor interaction between the bosons and work in a limit where U is really, really large. Okay? And there one can have a broken U1 symmetry in the superfluid phase and a broken translational symmetry in the Mott phase. And the nature of phase transition in this kind of systems has been a matter of debate. Now it's probably understood that it will still be a first order transition, but at some point people were thinking that it could be an unconventional second order type of transition. But what really happened in the field apparently is a much simpler way of realizing this kind of systems, this translation broken system. And this is a bit unusual, so let me try to explain it. What people do, the experimentalists, they came up with the way to shift the center of the trap holding the bosons. Okay, so you see that if you move the trap a little bit, the bosons now, this blob now moves to the left. Now, this trap is like a quadratic potential, and shifting its center means that you are allowing for a linear potential in your system. So, instead of half kx square, if I have a potential which is like half kx minus a whole square, I have a linear term in my system. And a linear term in the system of any quasi-particle is like an electric field. So that's why they call it electric field within quotes. It's not an electromagnetic field, it's just a linear potential that you create for these bosons. Another way of creating this linear potential is to apply a spatially varying magnetic field. And that's because all of these atoms, particularly the 87 rubidium ones, are in a f equal to 1 state. And then we see this Zeeman term, and if this magnetic field is linear, this again gives a linear potential. So initially people were using this technique, and later that, because this allows for better control. But nevertheless, at the end of the day, what happens is that you have a bosonic Hamiltonian, which is a linear term in your along with this chemical potential. Okay. So that's tilting this lattice, and that's like putting an electric field. So actually, this Greiner and others in 2001 did an experiment like that by regarding the tilt. So what they did was again ramp up this lattice potential, and then they subjected it to this perturbation where they put this tilt by removing the center of the trap. Okay, and then after this, so this is done for 20 milliseconds, and after that they lowered the trap a little bit, so that the particle, the bosons here essentially is in a superfluid state. So they let it be in that superfluid state, and then they do the momentum distribution measurement. Okay. what happens is that because these bosons have absorbed energy because of this perturbation, when they come to this superfluid state, that energy shows up and your central peak is split. Okay? And the more the energy, what they showed, the more the energy absorption, larger the split of this central peak. So by measuring the split of the central peak, they are going to find out how much energy is absorbed due to this perturbation. Interestingly, in the superfluid phase, if this V naught corresponds to the superfluid phase, the strength of this perturbation almost grows linearly and then saturates as a function of the field, that is the perturbation strength that is applied. However, in the Mott phase, it seemed that there is a resonant state because energy is absorbed only for some very specific perturbation, okay, out here. And so what they noticed and what we thought about at some point is that there seems to be a sharp resonant absorption at fixed electric field amplitude, indicating a definite quantum state in the Mott regime. And one question is, what is that state? What can happen?
Sorry, the K equal to 0 is split into 2.
Yes, because if you absorb energy, because you are not distinguishing between K and minus K, it has to split symmetrically. That's the, okay. Yeah. I'm sorry?
Is there any connection of these to star clad?
There is, I'm going to come to that. Okay. Just give me 1 second. Of course, as you have figured out already, that once you have these bosons and you apply this electric field, it's really a stark problem. The only thing is that there is also this interaction, which you need to be careful about. So let me just show you that. That's precisely the point of the talk, actually. So we wanted to think about what can happen here. So this is a cartoon picture where we have tilted the lattice by applying a field, and let's say that there are 2 bosons per side. You could have taken 1 boson per side, it really doesn't matter, a fixed number. And we are going to work in the regime, and this is chosen by the experiment, where the difference of U and this electric field and the hopping is small compared to both the electric field and U. And I would like to sort of stop here for a moment and point out that this is a regime which you never ever see in a standard condensed matter system, because electric field in the order of a interaction in a strongly interacting system, that's going to give you electric breakdown much before you reach this regime. So you don't see this but here you can come to this, you can realize this regime. Okay. Oops. Yeah, okay. So now the question is that what happens when you put an extra boson on top of this thing in the tilted lattice. Now, of course, there is an energy cost, that one can easily calculate. But there is also this thing that does this boson hop between sites to neutralize that energy cost, And when you try to compute that, you see that, of course, it can hop from side to side, but now it will also see this electric field, and this is a one-year stuck problem for these excitations, okay? And as you know, in this kind of situation, this one-year stuck problem essentially gives you a completely localized wave function, and so the boson doesn't move. And this is one thing that quantum mechanics predicts, which is completely different from the classical scenario. In the classical scenario, think of a lot of balls in a bucket, in buckets, and then you tilt this whole bucket system. The balls are just simply going to move and go to the last site. That's the classical result for you. So everything is going to sort of go in there. This doesn't happen in quantum mechanics. Another way of looking at this is from the block band picture, where you are going to simply get reflected from the edge of the Brillouin zone. You can also think of it in that terms. But nevertheless, what happens is that these things don't hop, they are localized, and therefore charge excitations are all strongly localized in the plane perpendicular to the electric field, and this wave function is periodic in time, and it simply gives you block oscillations. So quasi-particles and quasi-holes are not accelerated to infinity, and that's a very important point out here. Okay. So what are the excitations which can be resonantly close to the original Mott state, so that there is an energy absorption? Yeah.
Is there a situation, and by that I mean choice of coupling constants, where you have a stable exchange
Here it's difficult actually. Age states meaning I don't really know if the block.
You do have a ladder, but it has a beginning and an end.
Yeah, but not a very sharp one. That's the whole problem because there is a potential. You see, so yeah, I understand what you are saying, but the point is that there might be some interesting physics at the edge, but in this kind of systems, it's very difficult to probe it. So people generally talk about the bulk. I haven't looked into what happens in the edge under these circumstances. So yeah.
I mean, I only bring it up because it looks like you are interested in things like conductivity and.
Here, conductivity. You see, the point is that one thing to remember: this is not really electromagnetic field. So it's not conductivity in the ordinary sense. I'm interested in finding out states which are really close to the original Mott state. Bosons are always localized, but is there another state which is resonantly close to this original Mott state? That's what we are after. And the conclusion of this is that states with one additional quasi-particles or quasi-holes is not the state which is resonantly close. Okay, so that's the. What is resonantly close are these neutral dipole excitations. So imagine that you take one boson from one side and put it on the next. This costs an energy U, of course, because you are now changing the occupation, but it also leads to gaining of energy, which is order E. Okay, so this process, this excitation costs an energy U minus E. So this is a neutral dipole state because you are not changing the total number of quasi-particles, and these have, so if you bound these two, that's a dipole excitation. Now, one point is that two dipoles are not nearest neighbors because you can show that this costs an energy 2 times, it costs an energy, sorry, there is a typo here, it costs an energy U minus 2E, but you could create dipoles at sites which are not nearest neighbors. Yeah. Oops, what did I do? Okay. Okay, yeah, sorry. These are spatial positions inside the well. That's sort of, it's a cartoon. Okay, it's not like occupation of a state. It's just, it's just a cartoon to.
And they cannot occupy the same position.
They can. They are bosons.
That would minimize the energy.
Here, no, it won't.
Because you said it costs energy because
No, because you see the point is once you have started from a Mott state, you cannot move the bosons because all of the bosons wave functions are exponentially localized because of the electric field. It's just 1 year start problem. So you cannot. I mean, in fact, you can show that you can create dipoles at neighboring site, but not on the second nearest sites because that costs an energy which is way different from the original Mott state. So essentially what happens is that 2 nearest neighbor dipoles are not allowed, and so based on this, we tried to create an effective model in terms of these dipoles. Okay. So what is this effective model? So every dipole creation takes an energy U minus E. That's what I showed you. So if there are n dipoles, so the Hamiltonian has a U minus E times the dipole number, and then a boson, if it hops to the next site or if it hops back, it has a probability of creating and eliminating a dipole. So dipole number is strictly not conserved because of this boson hopping. Okay, and this has 2 important constraints. One is that you can only have 1 dipole per site because if you try to create the next dipole, it's too energetically costly. And you cannot have dipoles on neighboring sites, and that's the nearest neighbor constraint that comes in, because that's also energetically too costly. I'm sorry, once you?
Saying that once you create a dipole, then you cannot hop the quasi-particle further.
No, not anymore, because that's prohibited by the electric field. That's energetically too costly. And the only reason why you can provide this dipole at least one side is because of this interaction term. I mean, if it was just a 1 year start problem, you couldn't even do that. Okay. So, Dipole is a hole on one side, absence of boson on one side, and one additional boson on the next side. So you can just run. It's like an exciter, yes, sure, but a neutral one, of course. So now what we are going to see is what happens in the weak and strong electric field, and weak and strong here means that E being greater than U and E being less than U. So if the electric field is weak, the ground state is still a dipole vacuum, which is like the original Mott insulating state. You don't create dipoles because that costs an energy U minus E. And you can calculate some effective hoppings and stuff. And it turns out that the effective Hamiltonian for these dipoles is something like this. So there is a lowest energy excitation, which is a single band of this dipole excitation. The thing is not very different from a standard Ising model scenario. There's excitation soften as E approaches U, and this is a precursor of the appearance of a Ising density wave with period 2, and so higher excited states there is multiparticle continuum, and one can study those. Interestingly, in the strong electric field limit, what happens is that the ground state is the one with maximum number of dipoles. Because if U minus E is a negative quantity, you form as many dipoles as you can, right? But now I have already told you that you cannot form dipoles in neighboring sites, right? So there is this constraint that the number of dipoles on one site and the next is 0. So you can either occupy these dipoles on the odd links of the lattice or the even links of the lattice, but not both. Okay. So there is of course a Z2 symmetry, and the ground state breaks this. It spontaneously chooses either the even or the odd. And therefore, this is a Z2 symmetry breaking state, much like this Ising ferromagnet, where you have all up or all down. And of course, in between, it's not surprising that there is a Ising transition, from a garden variety quote-unquote paramagnetic state, which was like the dipole vacuum, and this Z2 symmetry broken state. And the reason why this transition has to be there is that you are connecting between two states, one with no broken symmetry, and the other one with a discrete symmetry broken, and this cannot be a crossover. You have to have a transition in between. So, and that's the quantum phase transition. So this is an example where this kind of things can give you another quantum phase transition, now all inside the Mott phase. Okay. And thankfully there are some experimental realization. And to understand that, let me just tell you what these guys did. This is done in Marcus Griner's lab at Harvard. And so apparently they used a different measurement technique, because this is all inside a Mott phase. Your momentum distribution is not a good way of measuring things, because we don't have a superfluid and it doesn't give you much information. So what they did is that they prepared the state of this 87 rubidium, so roughly 10 to the power 5 atoms in this case. And they used a magnetic trap potential, and they project a square optical lattice with and the lattice depth. Okay, so you get into a Mott state. After the state is prepared, whatever state they want to prepare, they essentially increase the lattice depth arbitrarily high, so that they freeze the atoms and over a large time scale. And then they apply light, and this light is applied in such a way that if there are two atoms on any given site, they can interact with this light and eject themselves out from the trap. However, if there is a single atom, it doesn't see the light. Okay? So there is this light assisted collision which eject a pair of atoms from each side. So if you have an odd number of atoms on any given site, you will have one left at least after all these collisions has taken place. If you have even number of atoms on a given site, you are going to have 0 atoms left because all of them are going to be ejected. So in this way they can detect the parity of occupation of the bosons inside the trap. Okay, and this is very useful. The reason being that so momentum distribution doesn't tell you much about the state of these atoms inside the trap in the Mott phase. This thing does. Later they actually tried later they did more with this, and they could actually measure the occupation number, but I'm not going to talk about that. This is good enough. And then they looked into this tilted boson system. Okay, and so I'm just going to show you this. So where this tilted boson with one boson per site in their language, because they wanted to talk in the language of spins, in their language this is sort of like the paramagnet, and these two bosons per site, this is sort of like an antiferromagnet. So our language was the transition from a uniform mod state to an sort of pairwise boson states, and in their language this is sort of like a paramagnet to antiferromagnet transition. Interestingly, the parity of occupation is completely different. So you are going to use, so when they measure this occupation, they are going to see a strong signal for the paramagnetic phase and almost zero signal for this antiferromagnetic phase. And the strength of this signal is what they measure, and they see a transition, and this is reversible. So if they change this E out here, which is this tilt field, they can bring it back. Okay. So this was sort of taken to be the proof of existence of these two states in the trap. Within the trap, within each lattice site. The position is a position within each lattice site. Yeah, I'll stop whenever the clock runs. So there is I know I'm not going to finish everything, but let me now come to the next part, which is this Rydberg atoms. Okay, so this is another platform again with 87 rubidium atoms, where people utilize the ground state of these rubidium atoms, which is this 5s, and an excited state, which is 71s. It's really excited, and they selectively couple these states to an intermediate state E using two lasers. Okay, and the reason they want to do it is that the interaction between two atoms, when they are excited in this Rydberg state, they have a van der Waals kind of interaction, and that's given by 1 over r to the power 6. Okay. So this V can be tuned experimentally. So the point is that if you tune this V such that the neighboring atoms see a very strong van der Waals force, you can prohibit Rydberg excitation on the neighboring atoms, or the next neighboring ones if you make it larger, and so on. So this phenomenon is known as Rydberg blockade, that if you create a Rydberg excitation on one of these atoms, you cannot create it on the next or within a radius of your choice. And using this Rydberg blockade, you can have some very interesting strong correlation physics, because this is like a constant that you put in. Okay? And what I'm going to show you is that it's not very different from the constant that has been put for this tilted optical lattice. But so the effective Hamiltonian for this kind of things is that the following. So there is a coupling term between this Rydberg and the ground state, which comes because of these two lasers and can be derived as a perturbative effective coupling, depending on this detuning, some atomic physics calculation which can be done. Then there is an energy cost, typically called as detuning, which is like a chemical potential for forming these Rydberg atoms, and the lasers can be tuned so that this delta can be either positive or negative. So positive delta means that you selectively want to perform, sort of create these Rydberg atoms. And then there is this term, which is this interaction between the Rydberg atoms. The point is that once you do this, and if you take your detuning to be large and positive, then for a standard value of V, you can be in a regime where you don't allow Rydberg excitations on the neighboring site. But delta is large and positive, so the system of course wants to form as many Rydberg excitations as possible, but it can only create half of them, okay? And therefore there is again a Z2 symmetry breaking spontaneously. It can either create these Rydberg excitations in the odd site or the even sites, and therefore it's again like an Ising ferromagnet, okay? And then of course if your detuning is small or negative, then you have a disordered state where most of the atoms occupy the ground state. So there is again a transition which is this Ising universality class, okay? So this physics is something that people understood. What was surprise in this original experiment is that they prepared the state in this Z2 ordered state, where there is this Rydberg excitation in every alternate site, And then what they did is that they quenched their parameters, okay, and put this delta to 0. That is, the detuning is set to 0, and they evolved this only with the hopping term, okay, and the interaction term of this. And this, what you typically expect, that because this is a interacting non-integrable system, the system is going to go to a steady state, a thermal steady state very quickly. Instead, what they saw is quite this long-lived oscillations, and this is this. So, okay, why do you expect this? Because there is something called, and I'm going to come to this in a moment, is something called eigenstate thermalization hypothesis, which tells you that for non-integrable quantum systems, you get into a thermal steady state very soon in all this kind of quench experiment. So this long-lived oscillations, which is not expected from the prediction of this ETH, is taken to be a violation of this. And this opened up a new field of research, which I'm going to come to next. Okay. And just one more thing before I go to that part, is that you can do a mapping of these Rydberg atoms in the language of spins, and at the end of the day, it can be mapped onto this Hamiltonian, where this, where you have this sigma x and sigma z, which is this Ni, and with the constraint that there are no two up spins on neighboring sides. And this is exactly the same physics as the tilted lattices. Okay. So now, and also, okay, so before going that, I must say that after that, people have, so this was for a Rydberg chain of atoms. For 2D atoms, there were many studies, and people found a lot of interesting phases out here. And there was a paper from Ashwin's group in which basically studied this on a Ruby lattice, which is sort of the midpoint of a Kagome. And there they essentially showed that, well, at least they claimed that there is a spin liquid phase out there. Okay. So interesting physics can happen with these Rydberg systems, but I'm not going to talk about this higher dimensional stuff. So now, so how much time do I have? 15 minutes? Yeah, okay. So I'm just going to finish soon. So now, because we saw some interesting thing in the dynamics of these Rydberg atoms, let's just talk about the dynamics part. And here, I'm going to first introduce one more thing, where statistical mechanics and quantum mechanics needed to be, was sort of pitted against each other. But let me tell you what this means. So consider a generic state of a quantum non-integrable many-body system. So I can always write this wave function in some eigenbasis. Okay. So this is perfectly allowed. And therefore, if I take the time evolution of a generic operator, this can be written in the following form. And then if I take the diagonal and the off-diagonal form, I can write it as this, where OMM is the expectation value of the operator within the energy eigenstate M, and OMN is the matrix element between two energy eigenstates M and N. Okay. Now when you look into this and stare at it for a moment, you see that this is not exactly what a statistical mechanical situation, a statistical mechanical analysis which we expect is going to give you. Why? Because the steady state value of O of t now depends on the overlap coefficient. So imagine that I go into the steady states where all these temporal fluctuations are now gone. If I wait for long enough time, I just have this answer, right? C mod Cm square OMM. But look, this depends on Cm, and therefore what it means that it has initial memory of the initial state of the system. And that's not what StatMech tells you. StatMech tells you that in a non-integrable system, once you traverse this entire phase space and stuff like that, the system completely loses any initial memory. So here, there is an apparent contradiction between the prediction of simple quantum mechanics and the standard StatMech system. The second thing is that it takes an incredibly long time to reach this steady state. Why? Because you see, when can you ignore this fluctuation? You can ignore this fluctuation when this time, t, is of the order of this energy gap. But in a many-body system, at least in the middle of the spectrum, the energy gap is exponentially small in system size. And therefore, you need to wait a time which is exponential of L, which for a reasonable large system is more than the age of the universe, to reach this steady state. And that's certainly not something that we see in the laboratory. Okay. So these two apparent contradictions are something that people were thinking about. And one way to understand this is to invoke something called random matrix theory, because the prediction, just saying that well, these states are too complicated and I'm going to just approximate them by some random eigenvalues and eigenfunctions, and if you do that, it turns out that this OMM is equal to O prime and OMN is 0. That's the prediction of this random matrix theory for a generic operator. Okay. And if that happens, of course, then you see that, your OT is just O prime, which doesn't depend on the initial memory. And of course, this thing is 0. But the point is that this provides an energy independent answer. Okay. No matter what the average energy of your system is, you are going to get this answer, and that's not what StatMech tells you. StatMech tells you that this expectation value is going to depend on the energy of the system, of your initial state. Yeah? Averages out to 0. Temporal fluctuations. So at very long times, it should just average out to 0. That's all I'm saying. Okay. But that time essentially is exponential, and that's not what you see in the laboratory. Yeah.
So this averaging to 0, is that some kind of a corollary of embodied hypothesis?
Yeah, you could say that, but see, I mean, I was thinking of a much more simpler thing, that if I have a temporal fluctuation and if I wait for a long enough time, where this T is much, much larger than any energy gap that you are going to save, I mean, this fluctuation is going to average out to 0. It's just,
So it's all very well to have that intuition to start the game, but it's another thing to see it play out. Right?
yeah, I understand. Yeah, sure. But so what you can see is that this kind of, okay, so, but let me just tell you that this is not what comes into play. So I'm going to show this. Yes, I'm going to show one. At least not the off diagonal part, but the diagonal part I'm going to show one example.
But why is waiting for a long time, but oscillating from periodic right? Why is this thing, why do you say that we should wait for a long time?
It's in some sense because of that. I mean, if you average over all phase space points, this just tells you that off diagonal terms are going to go away. Right? Okay, so to understand this, there is a generalization of this random matrix theory result, which is for a typical operator, which is due to this Deutsch and Srednicki and others. And apparently, they proposed that for a generic operator, which is reasonably local and has all good qualities, OMN for any states M and M would have a piece which is diagonal, which depends on the average energy of this state. And by average energy, I means expectation of Hamiltonian in the initial state. And this part, which is exponentially suppressed, this S is the entropy. Okay. And in the middle of the spectrum, this entropy is extensive, and therefore this suppression is very large. And this cures the problem, essentially. And one can show this. I don't have time. I'm not going to get into the details of this. But one can show that if you take this hypothesis, then putting this back out here, if you just take a d of t ot, take the long time limit of this O average, it just gives you the microcanonical ensemble answer. Okay. So, and that resolves the conflict with the StatMech. And here is an example. So StatMech predicts that this thing is going to be just a function of energy with 0 spread, but that's for a thermodynamically large system. Here this is done for a finite size system. That's why this red dot is a large spread. But if you take an integrable model where this kind of phase space things doesn't work, you see the spread in a similar type of system. It's exactly the same system with the interaction turned up, which makes it integrable, and the spread is humongous. Okay. So this this kind of systems, essentially this eigenstate thermalization hypothesis essentially provides you with this red line, which is consistent with the prediction of statistical mechanics.
So classes, I imagine also classy systems will not
Glassy systems is another beast. I mean, because the time, for those kind of things to put through this entire phase space is humongous. And I don't think ergodic hypothesis is going to hold at least in the experimentally realizable time for that kind of system. So I am not going to say that it's going to work for class A systems. It doesn't work for many-body localized systems, this MBL and other things. It doesn't work for integrable models. Those two are standard violations of this eigenstate thermalization hypothesis. What I'm going to show you is that another violation of this hypothesis, which occurs because of a special class of eigenstates in the mid-spectrum, which has a way of violating this hypothesis. And that will be the last thing I'm going to talk about. Let me skip this. So, these class of states are known as quantum scars. Okay? And these are special kind of states which essentially are in the middle of a spectrum of a many-body state, but they are not thermal states, in the sense that their entanglement is not extensive and stuff like that. Okay? So the simplest way to understand this scar state is with this lattice model. Okay? So I have a spin 1 so I have a spin 1 model where there is a xy term and a magnetic field. Okay? Now, of course, let me choose a set of parameters where the ground state is all -1 for all states. Okay? So that's this state out here. So for the spin 1, the states are +1, 0, and -1, the 3 mz state. And I'm going to choose this -1 to be the ground state at all points. Fine. Now I can create a magnon out of this by flipping one of these, so creating a 0, and then this 0 can propagate, and you have a magnon band and all that, but let me not get into that. There is another very interesting thing, is that you can apply an operator, something like this, which is s plus square, okay? Which means it's going to take this minus, and essentially it's going to create a plus out here. So this minus would go to plus plus, okay? If you consider an operator with an opposite sign of this s plus square on the even and odd sublattice, it turns out that this things is this term annihilates this particular state. The reason is that, and let me just do this very quickly. The reason is that this s plus square acting on a, let's say there are two of this minus, and it acts on this state, j plus 1, and this is j. So it just gives you a state which is plus minus. Okay? It acts twice and transfers this. Now think of a term which is like s plus, s minus, which is basically this term out here. Okay? The combination of this is just some s plus s minus term. So what is this going to do? This s minus is going to act on here, give you a 0, and the s plus is going to act on there and give a 0. So it's just going to give you a 0, 0. Okay? But now if this s plus square comes with the opposite sign on the odd and even sublattice, these 0 zeros from odd and even sublattice is simply going to cancel each other. And therefore this term essentially cancels, and you have a band of states coming from whose energy depends on this SZR, and this energy is the number of the such pairs that you have created. Okay? This set of states essentially is like a spectrum generating algebra. If you take this j plus to be your q plus, you just simply generate these states one after another. And apparently it turns out that this j plus and j minus, they form a SU2 algebra, and therefore there is an emergent SU2 symmetry in this model for this class of states. So it's a subset of states within your entire Hilbert space which has this SU2 symmetry. And therefore once you start in this subset, this symmetry prevents leakage of states into the other part of the Hilbert space, and therefore you have ETH violation, because it simply doesn't move through the entire phase space. Okay? Interestingly, what happens is that in the Rydberg atoms, there is an approximate SU2 symmetry generation like this. Although this is approximate, and there is no, to the best of my knowledge, there is no analytical foolproof scenario of this. There is some approximate way of tackling this, but I'm not going to get into the details. And it turns out that these kind of scar states has a huge overlap with this Z2 state, that is, Rydberg, no Rydberg, Rydberg, no Rydberg, that kind of Z2 state. And if you start from there, you see a huge oscillation which is due to these scarce states. On the other hand, if you state from a vacuum state, which is like all ground state stuff, you see ETH just gives you this steady state, and there is no. So this is one of these examples where you see that there is this violation of ETH due to this quantum scarce, and this ultra cold atom platforms gives you a very nice way of seeing this. Yeah.
You already say what a scar is?
Yeah, so these class of states is what I am calling this quantum scarce. Okay, that is, this is a subclass of states which has an additional emergent symmetry which protects it from the rest of the Hilbert space.
A scar is a subset of
Yes,
original state.
that's right. In this context, yes. So it has some classical root, why it is called a scar and all that. I'm not getting into the details, but we can talk. I mean, this, yeah, sure. Do I have 5 minutes or am I done?
Take 5 minutes.
Okay, thank you. So I'm just going to show you one last thing to just complete this part 3, which is that this kind of quantum scars not only appears in the standard setting where you have a quench dynamics, but it also occurs when you have periodic dynamics. And regarding this periodic dynamics, everything is controlled by this quantity called the Fluke Hamiltonian of the system. So instead of looking for scars into a Hamiltonian of a system, we are simply going to look into for scars in the Fluke Hamiltonian of the system. And this is a work that we did long time back, and I'm not going to get into the details of this. I'm just going to show you some phase diagram and stop there. So, okay, so maybe a little bit details would help. So let me get into this. So because the Fluke Hamiltonian is important, it would be interesting to see what happens, when you try to calculate this. And this is not an easy thing. It can be done within some perturbation. And it turns out that in this kind of system, this Fluke Hamiltonian turns out to be something similar to the original Hamiltonian, which was this, this sigma x tilde, but with a term which depends on this drive frequency. Okay. So if this gamma, which is this dimensionless drive frequency, and lambda is the drive amplitude, becomes integer multiple of pi, this HF1 goes to 0. And then there are higher order terms in Fluke Hamiltonian which propagates the dynamics. But when HF1 is present, that's a leading term. And we know from our original scar picture of this, of the PXP model, that HF1 essentially supports scars, but these higher states, they don't. Okay. So as a result, what happens is that you have a phase diagram where you have a regime where there is where this HF1 goes to 0, and you have thermal physics, which is the ETH obeying physics, and then this place where HF1 is not 0, you essentially see this coherent oscillations. Okay. So there is a tuning of coherence in a driven many-body system. Okay. So that's one thing which, so this driving frequency provides you with a knob of realization of these scars in this driven many-body system. So I think I'm, over time, so I'm going to just stop here. And so to conclude, what I would like to say is that these kind of systems, these platforms, provide you with an interesting setup where you could see closed quantum system dynamics and correlations, which is very difficult to otherwise obtain in standard laboratory practice, because standard laboratory setup, because the environment essentially is always there, and these are some of the most well-shielded system in the universe where you could see this closed quantum dynamics, I mean quantum mechanics at its full play. Okay, so I think I'm going to stop here, and thank you for your attention.
Questions? The last part went very quickly. So what
Yeah,
was the
sorry.
periodic drive with the Fluke one?
Yeah, so I can. So see, the point is that so we take this lambda to be large. Okay, so this U0 is the 0th order evolution operator, and then we compute the first order calculation, and that gives me the first order Fluke Hamiltonian. So this, you see, is almost like a PXP model in some rotated basis. The sigma x tilde is the projected spin and all that.
What exactly? So that sigma z is what is driven periodically.
Yeah, exactly. Yeah, it's the magnetic field term which is driven
Okay.
periodically. Yeah, that's it. Yeah. And then what you see here is basically that, once you have these terms, even at slightly lower frequency, you have these oscillations. But at slightly higher frequencies where this is close to m pi, you don't see any oscillations. And that's the phase diagram that I showed you actually. That's the phase diagram. And the other thing, the last thing that I would like to say is that once you get into these, you see that at this omega d equal to 0.5, you still see some scars, these red ones which are away from this thermal band. However, at 1.3, for example, you don't see them at all. They are all in the thermal band, and these red dots are what contributes to aerodynamics. Okay. So, and for omega d equal to 100, you see these scars. For omega d equal to 0.001, when none of this perturbation works, you see that everything is in the thermal band. So,
Even in this omega d equal to 1.3, there are some states that seem to have been pulled out from the middle spectrum, which have low entanglement, but they don't couple
but
to
they don't
the.
contribute to the dynamics.
Yeah.
These have another interpretation. I didn't get a chance to get into this. These have some overlap with the zero sector.
Yeah, some other initial
These are Fouquet scars, but they have overlap with the zero sector, and we saw this in later.
So some other initial state can, in principle, couple to this.
The zero,
Zero.
the ground. Yeah, the ground state couples to those.
So in this last part, so if you have a driving potential, so you showed these thermal states that are coming out. So does it depend on what initial starting eigenstate you take?
See, the point is what depends on the initial starting state is whether it's going to have an overlap with the scar states and show this oscillation. So, for example, if I
Initial state is not an eigenstate. I mean.
initial state is not it's not an eigenstate. Otherwise, there will be no dynamics. Right? It's a Fock state, and for the ground state, which is all this down, that Fock state gives you this ETH-like oscillation. That's a red dot for you. Okay, but if it's this other Fock state, which is this Z2, it gives you these oscillations. Okay, so that's the initial state dependence. It has to have an overlap with the scarce sector to see these oscillations.
When you show this thermal band, there there it is
Even this-
insensitive to the choice of your initial.
No, this is for the Z2 initial state.
Okay.
Otherwise, you are not going to have this coherent regime. I mean, because there is no scar-induced oscillations. And this is why it's called a weak violation of ergodicity, because it depends on the choice of your initial state.
So maybe you said it, but is this the lowest energy configuration, part of that, the splitting up of the, like into the scar state and something else?
No, it's not a low energy. You see, these scar states essentially span a tower of states, and this is mid-spectrum, high energy, low energy. It's just a tower like that.
And so it has zero coupling with the rest of the states.
It has in this case it's strictly not zero. There is a finite leakage rate, but that is small, and it's small because there is an approximate SU2 symmetry that emerges out here.
But
That
it can be
symmetry-
made exact also? Like
Sorry?
It can be made exact also?
In other models it can be made exact. The XXZ, this XY model in a magnetic field spin one that I showed, there it's exact.
But otherwise it's a metastable state with some lifetime.
No, the eigenstates are real, but the oscillations, they are going to decay after some time because there is leakage to the thermal sector. So you see, the oscillation occurs because the weight is mostly in the scar sector. But the scar sector, if it has a leakage to the thermal sector, these oscillations are going to die down after some time.
Which is a dissipation or what? I mean, it's not part of the unit.
It's just approach to the steady state. You see,
Okay.
how fast you approach to the steady state depends on this leakage rate.
But the entire thing is a unitary system, is it?
Yes, absolutely, yes.
Okay.
But
Then
even
it should be a
unitary,
metastable state, no?
no, even unit, we call it pre-thermal, but you can call it metastable.
Okay.
So it's what happens to this system essentially before it approaches the thermal final steady state. So that's so there is a wide pre-thermal regime where this kind of oscillations are seen, and then everything decays. Okay.
Anything else? Yeah. Okay. If there are no further questions, let's thank
Yeah, thank
Krishnendu
you.
again. So there is now coffee outside, and we reconvene at 11:15. Yeah, now it works. Okay. There's green light there. You just test?
Hello. Yeah.
Hello? Yeah, okay. Okay, welcome back. It's working, thanks. Okay, so now we have an experimentalist, so it's a pleasure to have Mandar Deshmukh from Tata Institute of Fundamental Research. Mandar got his undergrad degree from IIT Kanpur. He did a BTech in engineering physics. IIT Bombay, sorry, very sorry, yeah. IIT Bombay, yeah. And then went on to do a PhD with Dan Ralph at Cornell. He was a postdoc at Harvard and then came back to TIFR in 2006, where he has been ever since. So today he will tell us about Moiré materials for probing Berry curvature physics.
Okay. Yeah, it's great to be here at this meeting, and I'm happy to talk about. Mostly, it will be a pedagogical talk of the field, and maybe in the last 15 minutes, I will really talk about an experiment which sort of will exemplify how we can actually measure the quantities that I will sort of present in the first 45 minutes or so. Okay, so this might seem like a lot of jargon for some of you who are outside the field, but I'll try to demystify these as we go along. So please don't be worried that I'm going to give a research talk. We gratefully acknowledge the funding that we get from different funding agencies of India, Department of Atomic Energy and Department of Science and Technology, that makes our work possible. Okay, so at the outset, let me make sure I acknowledge the collaborators and the students who I've worked with and who have taught me many of the things that I now know. My students, Subhajit, Pratap, they are both graduated, they're postdocs elsewhere. Surat and Aishi are students now, and I learned a lot of things from them. My collaborators are Umesh Wagmare from JNC, his group members, Amit Agarwal from IIT Kanpur and his group, and some key material that we get which makes some of these experiments possible is this hexagonal boron nitride. And its connection to what I'll talk about will become clear, is made by these two gentlemen at NIMS in Japan. So these are some photos from a treks close to Mumbai, mostly in monsoon, which make it fun. So these are the people I highlight. Okay, so this is my outline for my talk. Before I get started in my talk, I want to make acknowledge the meeting that Bhaskaran and Shankar had organized many years ago. We were trying to date it a few minutes back in the coffee break, and that was I think early, maybe 2008 or 9, which was the beginning of this 2D materials revolution and graphene, and that was quite a fun meeting, and that actually led me to go into new areas which I did not plan to when I came to TIFR. So it was really a very important meeting, and many of the things that I'll talk about have essentially sprung out from that sort of change of directions into more greener pastures, if you like. Okay, having said that, let me get started. So I'm going to talk about Berry curvature physics in the beginning and connect it to ideas of quantum geometry and topology. This is primarily for the students. Then I'll go into this newer field of twisted materials. So essentially creating metastable materials, take one atom thick layer of graphite, put it on top another 1 atom thick layer of graphite, rotated by a precise angle, preciseness is something like 1/10 of a degree or better, and ask what are the interesting properties and why is it interesting even. And that is a material which is called Moiré material, and that genesis of that name is from sort of beating pattern that you get if you have a mesh and another mesh and rotated by an angle, you see a beating pattern. That is Moiré. Then I'll talk about 2 examples of how you can use electrical transport to probe the physics of Berry curvature, which is related to these ideas of topological condensed matter. And then towards the end, I'll talk about some really new results from our lab where if you have a honeycomb-like lattice and you modulate the strain, you kind of put the honeycomb lattice on a trampoline and you kind of vibrate the trampoline, you basically get a time-dependent strain. And that time-dependent strain actually is a very interesting knob to probe sort of the quantum geometry of the system and also generate some pseudoelectric fields in similar as would be expected in sort of analogs in high energy physics. So this part will take very little time right towards the end. Most of my time I will spend discussing what is interesting in the first 2 parts. Okay, so let me get started with sort of the material which is sort of, I would say, a mother material which led to a lot of interesting physics in the last 20 years or so. So the material is graphene, which is essentially 1 atom thick layer graphite, and its sp2 hybridized bonds provide the mechanical scaffolding for the carbon atom. So intentionally I have colored the sites of this honeycomb lattice in orange and green. It will become clear in a moment, but they are occupied by the same chemical species in graphene, which is 1 atom thick graphite. So the sp2 bonds really don't play no role in electronic property, which is the focus of our sort of interaction or my talk today. And the electronic properties emanate from these p orbitals, which are unhybridized from the carbon, which are sticking out of the plane of the screen and 1 lobe behind. And when there is a sideways overlap, you form a kind of a new orbital which gives rise to these unique and exciting electronic properties. Okay. So coming back to why are these 2 sites green and labeled as green and orange, and the reason is that at a 0th level you might say that this sites green and orange are identical, but on a closer inspection what you realize is that there is some basic fundamental symmetry that distinguishes this 2 sites green and orange. And the simple question that distinguishes is, if you ask the site orange, is there a site on the right of site orange, and the answer is no throughout the lattice. And if you ask the site green, is there a site on the left of it, and that answer for that is no as well. So there is this left-right handedness in the lattice which is intimately connected to the properties, electronic properties that will emanate from this system. Coming to some technical terms, this is not a Bravais lattice. You need to start with a triangular lattice, and at the centroid if you put another site, you have to basically have a 2-atom basis, then you get this honeycomb lattice. So the starting lattice is a triangular lattice. Okay. Now, whenever condensed matter researchers are trying to understand the electronic properties, they will try to calculate the energy momentum relationship of the electronic states close to the Fermi energy. For most part, especially in the talk that I will be giving today, we are interested in right close to the Fermi energy. So if you think of the electronic sea as a very deep sea with lots of electrons as a function of energy, we are really interested in the ripples on top of the sea, much like the ripples close the sea not very far from here. We are not going to be worried about the electrons that are deep inside. So this is what the electronic states close to the Fermi energy, the Fermi energy goes right through this point, look like. This is sort of the conduction band, if you like, and the valence band. So the states which, and what you see is that this electronic states touch each other and at 6 points, much like the 6 points that are in real space here. This is the momentum space. So this material technically would be called a gapless or a semi-metal, if you like, because it doesn't have a gap between these electronic bands. And this is important, and the Fermi energy is going right through it. Just to give you a scale, this energy scale is electron volts, order of electron volts. And when we do electrical transport measurement, we just want to look at the tiny ripples close to it. So we are not really interested in the energy scale of electron volts. So we will zoom in very close to the Fermi energy and ask what is the structure of this energy momentum relationship, or right close to the Fermi energy. Okay. What you see is that although there are 6 points, the two neighboring ones are fundamentally distinct, and I'll say a little bit about it. Others are kind of mirror images of these two. Okay, so to understand the properties, what you really need to understand is just two of these. These are called two valleys, if you like. We won't go too much into why it's called valleys, but these two different valleys play an important role in understanding the physics. So if you zoom into one of these touching points, the electronic spectrum of the states looks like this. Is basically two cones touching each other, and this is sort of often in condensed matter we do this. There is sort of an emergence just because the electrons are not really free electrons, but they belong to the lattice and the symmetries that give rise to the electronic states. They reflect in the Hamiltonian that the system is described by. So we construct a low energy Hamiltonian. So this is not a Hamiltonian at all energies, but close to the Fermi energy, which is sort of the top of the electron sea. This Hamiltonian is a very good description of the excitations that are inside. So at one of the band touching points, it is exactly like a massless Dirac fermion. Okay, you don't have velocity of light, but there is Fermi velocity, which is about 300 times slower than the velocity of light. And the other valley, which is the neighboring valley, which is fundamentally distinct, is kind of twisted, and that Hamiltonian is very simply just by a negative sign, or the effective low energy Hamiltonian that describes it. Okay, so this started a lot of the interesting physics discovery in this sort of 2D materials. Realization of interesting Hamiltonians is very easily possible in these kind of condensed matter systems. In some ways, you can think of these, as I will show later in one of the slides, as also a platform to quantum simulate many of the other complex quantum emergence that we see in correlated materials. Okay, so now, yeah.
So is that sigma, that's the spin of the electron?
No, good. Thanks for asking the question. I was trying to sort of go ahead, but it's not the spin, but it's actually the fact that there's two sublattices in the system, and that's it's not really spin. Real spin of the electrons plays no role in graphene because there is no spin-orbit interaction. Is this two orange, and is basically connected to this idea that there is this two different sites. Yeah. Yeah. That's right. Okay, so moving on, one of the beauties of these kind of systems is that nature itself gives sort of realization of different kind of effective low energy Hamiltonians, if you like. So I gave you an example. Same lattice, honeycomb lattice, you have carbon atoms, it preserves some symmetry. Then another cousin of that, which is the material that I thank the Japanese collaborators for, is hexagonal boron nitride. Again, honeycomb lattice, exactly the same lattice, but now alternating atoms are boron and nitrogen, which are on either sides of carbon. So pairwise, boron and nitrogen are isoelectronic with 2 carbon atoms. So the number of electrons is net, gross is the same, but these are 2 radically different electronic systems. The upper one, graphene, is a semi-metal good conductor, whereas boron nitride is a very good insulator, which is with a large band gap. So for graphene, the low energy Hamiltonian is the massless Dirac fermion. For other materials which break this important symmetry, inversion symmetry. So if you look at this honeycomb lattice about the center, if you do an inversion operation, graphene carbon goes to a carbon site, inversion is preserved, and whereas in boron nitride, inversion symmetry is broken. So the moment inversion symmetry is broken, you open up a gap in the electronic spectrum. It's no longer gapless system, but it has a gap, and the effective Hamiltonian that described is that of massive Dirac fermions. Okay, and this important role of how symmetry allows you to engineer electronic properties is also seen in one of my favorite examples in this field. This is work done in the early days. If you have 2 layers of graphene, you have 1 layer of graphite and one layer of graphene and another layer in this AB stacking. Okay. Now, and you make a electrical device out of it. So the way the electrical device is made is you make contacts to it, and I'll briefly explain that a little bit later. And then what you can also do is you can apply a perpendicular electric field, which is not for sending the current through it, but by essentially changing the potential that the 2 layers see relative to each other. Okay. So when you don't apply an electric field, the electronic bands of bilayer graphene, you have these copies of Dirac cones, they hybridize further, and you get these parabolic bands. Okay, they are different from the massless Dirac fermions, but they are also gapless, because overall the system has inversion symmetry. I will show in a minute. But the moment you apply an electric field perpendicular to it, the potential of the sites here and sites here are no longer the same, and the system actually becomes inversion symmetric broken system. Because if you look, this is sort of the cross-sectional lattice. These are the 4 sites. This is the upper graphene, this is the lower graphene layer. And when you apply an electric field, the potential seen by this site and this site are no longer the same. So if you do inversion, in the presence of an applied perpendicular electric field, you break inversion symmetry. And when we break inversion symmetry, we open up gaps in the electronic spectrum. So what this is a system whose electronic properties can just be changed in the same device by applying electric field. You break some symmetry. Now something which was a semi-metal is now a semiconductor, whose magnitude of this gap is tunable by applying the magnitude of the electric field, because that controls the magnitude of this asymmetry. Yeah, dispersion is quadratic because already the bands have hybridized. So I'm not going into too much detail because yeah, but you're right. There was another question.
What are the 2 levels that are shown there? The 2 blue ones, or
this one?
no? On
Here.
On the next, on the rightmost one.
These.
Yeah, the 2 blue.
These ones.
Or on the next one, to the left of that, right? To where you say
here.
Yeah.
Okay. All right, so I should stick back, and what I was trying to sweep under the rug, I should probably address that. So when you think of 2 layers of graphene, so if you have 1 layer of graphene, you have 2 Dirac cones, I explained. Now in bilayer graphene, you have another layer slightly displaced, and then there is electronic hybridization. So the new bands that come out of it are no longer Dirac bands, but which are linear dispersion, but they become quadratic. So you get this set of 4 bands, electronic states, but in the absence of inversion symmetry breaking, they are still gapless. So the dispersion is no longer proportional to P, but P square. Why? Because the 2 electronic graphene are electronically coupled. They are not, there's a strong hybridization, and that gives rise to these quadratic bands, and something that, that will happen. That's a feature of it. I wouldn't say it's a bug of the system, but the starting point is Dirac, then you have Hamiltonians, and then new effective low energy Hamiltonians will be born out of it.
So these are 2 lowest lying
Yeah,
states
yeah.
about. Okay.
Yeah, so as I said, we often condense matter people who are looking at electronic transport, there's a lot of complicated mess below and there's a lot of complicated mess above. We are simplifying things by looking at what's close to the ripples which we are trying to probe. Yes, I can tune it. So that's another beauty of it, that I can create a gap, I can move the Fermi energy continuously through the gap. This is the power of the kind of devices that you can do. I can control the electric field, and what in the material science community is called doping, I can independently control it. Okay, so this position of the Fermi energy is an independent knob that I can tune continuously through the system. Okay, so now when you break some symmetries, there are also other things happening, just not just a gap opening in the spectrum, but something deeper is happening to the electronic wave functions. And there's many decades of interesting, exciting work, and people about 20 years back were already coming to a good understanding of some new ideas on how to look at very disparate kind of physics, kind of put it together. So, and that's the physics of, you can call it by different names, but I will refer to it Berry curvature physics. So when you think of electronic bands, I have, similar to the bands I showed, these are just a sketch of not graphene or anything, but just general. I think of electronic states at a given energy and momentum, and I can think semi-classically, and I apply electric field, I'm kind of moving these wave packets inside the solid, while I apply electric field and the electron sort of moves around inside the solid. There's also a kind of a motion of these electron packets in the momentum space, which can lead to interesting and exciting physics, and that's sort of what I'm going to talk about. So in some systems, and I'll qualify that, these sort of wave functions of these electronic states have a kind of a self-rotation associated with it. So they're kind of twirling about their axis, if you like, and that's how the system responds to any external perturbation like electric field. Now, when is this self-rotation in some bands there? I will qualify in a minute, if you bear with me. Now, let's first discuss the consequence of this self-rotation. This is in the absence of any external magnetic field, just some symmetry properties of the system endow interesting and exciting properties. So this self-rotation literally provides a Magnus-like deflection for these electrons inside the solid, again depending on the symmetry of the crystal. So it's as if I am applying an electric field, but and the charged particle is responding semi-classically to the electric field, but now there is another component of the velocity which is different from the direction in which the electric field is applied. So when we think of this, we go back to simple semi-classical equations of motion for electrons in a band. I can apply an electric field and I can sort of think of rate of change of the momentum, and then there's another equation which sort of connects me to what is the consequence in terms of its velocity. And this term is the term which it comes about only because of this property of the wave function, which is this self-rotation, and this term is called omega, which is the Berry curvature. In most systems, so this in the early editions of, or certainly of Kittel, this term will not be there. It will not be there, at least written in this form, in Ashcroft and Mermin, and that's because this realization of understanding these properties in this way was not there. So most systems do not have the Berry curvature, it's 0. So these equations were written in Kittel and Ashcroft and Mermin, ignoring the existence of this term. But systems other than, of course, these 2D materials, it was realized that you have systems where this Berry curvature can be non-zero, and you have to take into account this additional velocity or the anomalous velocity to understand. So Berry curvature is non-zero when you break inversion symmetry or you break time reversal symmetry. Okay, so as I already gave you examples, in graphene-like systems or in bilayer system, it's possible to break inversion symmetry on demand, and you can get Berry curvature. And another interesting property is that the two valleys that are there, they have opposite sign of the Berry curvature. So electronic states belonging to one region of momentum are getting deflected with one component of the anomalous velocity. Electrons belonging to the other valley are getting deflected in the other direction. So that property is one hint that you can actually experimentally also test that this physics is not just a conceptual framework, but something you can actually experimentally measure. Yes?
Sorry, this is a single electron wave function that
yes.
you have described. And the rotation is about some other center or what? I mean, it's like, so the wave function, the way you drew it was a symmetric thing and there's no meaning to the thing.
That was just a sketch. The one that here, what I drew here is just a sketch.
Okay.
To motivate this self-rotation idea, it's a semi-classical qualitative idea to introduce this idea of Berry curvature. But once you have the eigenfunctions, most of the time in condensed matter physics, people just calculated the eigenvalues, draw the band structure, and didn't pay too much attention to the states, the wave function, especially when a gap is open, when the states get hybridized. That twirling is associated with the admixture of electronic states across a gap. And that's where the Berry curvature comes. Okay, all right. So an extension of this is ideas of this Chern number, which is sort of a kind of a sum over a whole electronic band of this Berry curvature summed over the Brillouin zone in 2 dimensions, which is sort of going to be of interest here because you have this translational symmetry. You use periodic boundary conditions, and so this looks like a cylinder wrapped onto itself like a torus. And so if you sum over this Berry curvature over the whole band, it gives you an important invariant, which is the Chern number. So Chern number, unless you do something drastic to the Hamiltonian, small perturbations are not going to do anything. This Chern number is non-zero only when you break time reversal symmetry of the system. If the time reversal symmetry is protected, the total Chern number of the band is 0 by simple arguments. However, when you have a non-zero Chern number, if you somehow manage to either apply a magnetic field and break time reversal symmetry, or spontaneously the system polarizes into a time reversal symmetry broken state, then you get a consequence of this non-zero Chern number is you have a topological or a boundary mode which is protected, and charge can flow around in a dissipationless manner. Similar physics will happen in quantum Hall as well. And then later on, interesting physics came out that even if you have a zero Chern number, this is work, Duncan Haldane and then also Kane and Mealy, that you can have interesting topological states of the system where the Chern number is zero, but you have two boundary modes which are circulating in opposite directions. Now, often people show the the picture of a mug and a donut all the time whenever condensed matter people want to do it, but the connection with this topological sort of ideas is that this invariant is a sort of a broad idea. Chern number, it's connected in lots of different physics. Chern number, it's also called the TKNN invariant, and it has deep mathematical connections which I don't claim to understand fully, but this is the connection that exists and connects this condensed matter to ideas from topology. Yeah.
A little general question. You are using the words like Dirac fermions as opposed to Majorana or Weil or whatever. Secondly, you are using is topological language. Within the condensed matter framework, what is the explanation? Forget the abstract mathematical terminology. How do you understand the invariant and why is it constant and so on? Within condensed matter itself, dynamically there should be explanation that is a lot clearer than going to topology and so on, at least to
the explanation, I mean, you are saying there is a boundary mode. So for example, in the quantum Hall case, I can start from, without invoking all of this, I don't have to go to Dirac fermions, but that is a special case that I apply a magnetic field. I think of these Landau levels being formed, and there is some chirality associated because of whether I am applying a magnetic field this way or the other way. Then I will get the semi-classical skipping orbits that will be formed at the edge of the material, which are what eventually give rise to these edge modes which live on the boundary of the system. In the bulk, you have the Landau level gap, and there is no transport inside the bulk. And the boundary, you have these Landau levels cross the Fermi energy and you get this topological boundary mode.
And this feature is arising because of what?
It's just because of let me draw a picture just to address your question. So these ideas are the same ideas. Instead of relying on an external magnetic field, you can think of it as Berry curvature, essentially time reversal symmetry breaking in and the Chern number from the Berry curvature being non-zero. So in a normal quantum Hall system, you have these Landau levels. I'm still talking about integer quantum Hall. You have this is space, this is energy. I have these are Landau levels. So inside, away from the edges, the system, a metal which continuous states breaks up into levels. So this is that. But when I include the existence that there is a physical boundary, these electronic Landau levels have to pop out because there is a large potential on the other side. So when they cross, this is my Fermi energy. When they cross the Fermi energy, I have a gapless excitation, which is a boundary mode. Okay? And if I now complete the picture and look at from the top in real space xy, I will have one boundary mode, another boundary mode, basically these guys circulating in one direction depending on the sign of the magnetic field.
So this is effectively a boundary effect, and therefore should be true for other materials also. You are specializing to graphene and two layers and so on and so forth, right?
Yeah.
So I'm trying to see what is the actual physical effect which is giving rise to these mathematical properties. That's what I'm trying to understand.
So it's the same physical effect. Instead of relying on external magnetic field, the structure of the Berry curvature is what really gives rise to essentially the same physics. So recently people have realized that you can have analogs of it, quantum anomalous Hall states in these kind of 2D systems where spontaneous symmetry breaking generates a non-zero Chern number. So there is an intimate connection between the physics of quantum Hall and physics that comes from the structure of the Berry curvature in the system. There is a fundamental distinction between the Chern bands and Landau laws, but there is a lot of things that you can go forward with.
Okay, we can continue
Yeah.
later. Yeah.
Can I just make one comment?
Yeah.
Regarding this, I think one good thing to sort of think about is that this is like having a vortex, but the vortex is now in momentum space. Just in standard superfluid, if you have a vortex in real space, you carve around that vortex and you gather all these things. Here, because of these Dirac points, it can be thought as a vortex in momentum space. Move around that and you get this term. So you can think of all of this as having multiple vortices in your Brillouin zone, and it's just the effect of that in the semi-classical.
Yeah, that's also another but equivalent way to think about it. Yeah.
Maybe another way that I can rephrase Ghanshyam's question is, would you see this? Would you see the effect of this more advanced mathematics if you worked with just a single layer of graphene? Do you need the second layer?
No. Okay. Yeah. As in single layer graphene, if I have other knobs to break inversion symmetry, I would still get it.
Yeah,
so if I put something that breaks inversion symmetry, I will see it in single layer as well.
Okay. So it's related to the breaking of inversion symmetry.
Yeah.
And if you didn't have that, if you didn't have those other knobs, then you wouldn't see the effect of this curvature and mathematics like this.
Yeah. So
is that have I misunderstood you?
I don't fully understand the question, but let me.
So let me ask. Let me take away the top layer, no, and I have just one layer.
Yeah.
That is already, I am told, a very interesting system.
Yeah.
Okay. But in that system where I have just one layer, would I see the effect of Berry curvature and?
So there is Berry curvature there. It's just diverging at the Dirac point, at a precise Fermi energy, at which the two Dirac cones are there. It's not that the Berry curvature is not there. It's there, but it's there at a very, very. This is one valley and this is another valley. It's right at this point. It's a divergence of the Berry curvature.
Okay.
Okay. So experimentally to see consequences of it is a little bit tricky because the local chemical potential in graphene can be varying because of disorder in the system.
Yeah.
So you cannot approach that point with this diverging Berry curvature.
But in real life or in experimental physics, things never diverge, right? They may become large, but they never diverge.
They never diverge, but to see the consequence which lives right at this meeting point is a little hard experimentally, that's all.
Okay.
Yeah, there are other consequences of...
Yeah, consequence of this chiral anomaly, which is manifesting dramatically when he applies boron nitride, when he brings boron nitride or inversion symmetry break. We can chat about it. In fact, the beautiful analogy with high energy physics and parity anomaly, chiral anomaly, all of them appear here.
Okay. Yeah.
How do we determine this omega?
How do you experimentally measure it? I'm going to... You can calculate it. It's a 2 by 2 matrix problem or a maximum 4 by 4. You can understand a lot of the properties.
What goes into that? I mean, is it like...
You can start with the Hamiltonian, tight binding Hamiltonian. You get, from there you can get the bands, dispersion of the bands, but you can, the wave functions, the eigenfunctions allow you to calculate the Berry curvature. Okay, so I won't spend too much time because I'm already running a bit late, but it has connection to this newer ideas of quantum geometry, which is quantum geometric tensor, which is essentially asking what is the distance of eigenstates, and this distance has two parts. One is sort of the real part, which is the of this quantum geometric tensor, which is the quantum metric, and then the imaginary part, which is the Berry curvature, which is really what I have been talking about. But in systems, people are increasingly trying to access and understand what is the role of quantum metric, because there are some connections to superconductivity in systems. So it's a kind of, what I want to show here is not to so mathematical structure, but to show that people are discovering some new ideas or new ways to think about physics which was not there. And these kind of 2D materials are playing an important role because there are all these knobs that you can apply a voltage, break the symmetry, to apply electric field, tune the Fermi energy. It's not possible in real materials. Okay. These are just different some labels which you can think of momenta or time, some parameter. When you look at the state as a different as a function of a parameter kappa, and different snapshots of it. Yeah, you can think of it in momentum space, but you can also think of it as more abstract as a parameter space in which you are looking at what's the distance between states as a function of evolution of a parameter in your Hamiltonian.
These are arbitrary points.
Some snapshots, that's all.
Not specific.
Yeah.
Parameters of the wave function?
I mean, in condensed matter, they are basically momenta, but you can also think of it in terms of some, let's say a magnetic field is a parameter of your system, and as you evolve the magnetic field, these are different magnetic, B1, B2, B3, B4. Yeah.
Positive vertex. Look at K prime, it looks like minus negative vertex. So that's also maybe the reason for the confusion.
No, here I'm just nothing related. This picture has nothing to do with specificity of 2D materials or graphene. It is general idea.
But in graphene, there's a vertex at K
Yeah.
and anti-vertex.
Yeah.
Yeah, here it's just a family of states in the Hilbert space, parameterized by kappa.
Yeah.
Then take any two of them, you can define a distance.
Okay.
What, mu? Yeah, so that depends on your parameter, 1, 2, 3, anything, yeah.
Yeah. If you'll excuse me, I have some experimental work to talk about. This is just to give a bigger pedagogical introduction to the field and the terminology. Hopefully, this has demystified a lot of the jargon. So let me get started. These 2D materials or Moiré materials, what is exciting about them? So way back in 2005, this is a slide that I love, not just because I'm an experimentalist, but because it's a power of kind of crazy thinking. Andrei Gaiman and Novoselov did something which most people thought was not possible, which is take a crystal of graphite and literally peel off a layer, and it's done using this Humble tool, which is a Scotch tape, which I'm sure all of you have at home somewhere. You take a tape, you put a crystal, and you peel off, and you do it repeatedly. Every time you don't get a single layer, like most things in life, you don't get it in the first go. You peel it off many times, and you experimentally dab it on different surfaces, and then what key role in this search for graphene and monolayer is played by our own C.V. Raman. Raman spectroscopy is a very powerful tool for telling whether it's a single layer or two layer. So you rely on stochasticity, on randomness and this experiment, and dab it on surface, and then you figure out how many layers it is, and then you make an electronic device out of it. So this sounds like a crude thing, but this is really sort of behind this revolution in scientific revolution is this simple idea that you can do things which most people think are crazy, and then you get something really lot of fun. And this is an optical microscope, a simple microscope image, which can be, you can see essentially assortment of thick layers of graphite. This is very thick. This is not very different from the graphite that comes out from your pencil and gets stuck in the paper. This is shiny, silver colored, very thick, more than 100 nanometers. This is few layers of graphene. This is thicker than few layers. And you see a triangular flap here, which is hanging out. It is precisely 1 atom thick. Okay. So how do I know that it's only 1 atom thick? Is that this is experimental science. You do this many times and you study its electronic properties and you use techniques like Raman spectroscopy, you know for sure that I'm not relying on randomness, but I know that it's one atom. Not just that, I can tell it's 2 atoms or 3 atoms. Okay, so this led to a revolution starting from 2005 to kind of an absurd level that you can pick up one layer of one material like graphene, you can pick up another layer of one layered magnet and another layer of superconductor, and you just stack them like a bread sandwich. So one layer is graphene, another layer of bread is another, and you put some sticking jam in between or chutney you like, and you make a stack. And this is precisely an image of that way back in now almost, it sounds way back, but 2015, you can make lots of layers thickness. And people made complex devices very quickly, something like 7 to 8 years after the initial discovery. So this led to a lot of revolution, and this connects to some physics that students will certainly love, which is the physics of chronic penny model, where you have this periodic 1D potential, and you look at what happens to electronic states which scatter off this 1D potential. And this 1D potential essentially changes how the energy momentum relationship. This has nothing to do with graphene, but this happens in general in most solids. So way back in 70s, people in IBM made this kind of a gigantic bread sandwich, not using 2D materials, but using semiconductors. This is a cross-sectional of that sandwich. You make one material, another material, and you just make a huge stack. And when you send electrons like this, you basically realize chronic penny model. And so that was a way to engineer the band structure, which is energy momentum relationship, by creating this alternating potential or designer potential. Now, after the arrival of 2D materials, there was a kind of connection to this physics, is that if I can peel off one layer of material, I can as well peel off another layer and rotate one layer relative to another. And do something crazy, just a minute, created a twisted structure. This is called moire. And if I take one layer of graphene and tear it and put it back at some angle back on it, there's a spatial beating pattern, not very different from the beating pattern of two sounds, but now there's a spatial beating, and the length scale that emanates out, it depends on the angle of the twist between the materials. These materials are metastable, they don't occur in nature because you're twisting them at angles which are 1 degree or 1.5 degree, but it can be experimentally done. This is another example of the creativity of the experimentalists to realize these kind of systems. Yeah, you had a question.
Yeah, this cheap and easy way of getting the graphene
using sellotape, it's fantastic, of course, but I was curious, what is the lateral dimension of the sample that you get?
Yeah, I'll show you more images a little bit. These are orders of microns. So by the spinning off method, these are good for electronic devices, but electronic devices for scientific curiosity and research, they are not scalable. Okay. Once in a while, you might get a very large crystal, but this is, lifetime of a PI like me, you might get a crystal which is 1 millimeter, but you can't run your lab based on that.
Typically, they are much, much smaller.
Yeah, its order of good number is less than human hair's diameter. Human hair is 100 micrometers.
Okay. And the second question was that when you stack these on top of each other, then it's the chronic penny model that you have in mind is the Z direction.
Till now I showed you was in the Z direction, okay. But with this knob, it is kind of a 2D version of the chronic penny model.
Okay.
Okay? If I put it in like Z axis, then it's the chronic penny model in Z. This is now a kind of an extended 2D chronic penny. Yeah.
So this pattern is actually, I don't understand what is moving here.
Okay, there is one layer of graphene. I tear
actually moving. I understand 2 layers are there at an angle.
This is just to show you how the periodicity, XY periodicity of this another length scale changes as I change the twist angle.
So as you change the angle, this change. That's what. Okay, fine.
It's just to illustrate that. It's made by a collaborator, it's a nice way to see the length scales. Okay, so this, just to give you a sense, this length scale is at a twist of angle of about 1 degree. This length scale of beating Moiré length scale is about 10 nanometers. Okay. All right, so how do we make it experimentally? If you're curious about it, we take one mother crystal of graphite and you cut of graphene, and you cut it into 2 pieces to create 2 daughter crystals. Then you kind of pick one insulator, which is sort of the boron nitride, and then you selectively pick up one layer, okay, not the other one. Then you rotate the system on which the remaining daughter crystal is by the angle of your heart's desire, and now this are derived from the same material. Now they have a relative rotation of what you wanted, and then you pick it up, and now you get a Moiré crystal of the angle that you want, and then you encapsulate it, bury it inside this boron nitride just to protect it from the complexities or disorders that you might have from the outside world. So this is kind of optical microscope image. So this is 20 micrometers. So the Moiré, which is this overlapping crystal, is about, roughly 15 micrometers. So that's good enough for us to do use techniques of nanofabrication to make many electrodes and probe the properties.
Sorry, the substrate itself does not change the properties.
Not zeroth order, no, but there are other ways. I want to keep the story a little simple, but the relative, you can form a Moiré between the substrate and graphene also. Maybe we discuss offline. So, going back to the single flake, we use ideas that have been developed from semiconductor nanofabrication like this to make complex devices by using lithography to make electrical connections. Hopefully this will play. Yeah. So how do you, this triangular flap is about 25 micrometers on a side. So how do to apply voltage, measure currents, I need to have several electrical connections to it. And this is sort of the method. We use a method which is effectively, if you have used a Rangoli stencil in your life, this is the Rangoli stencil, but with nanotechnology at your benefit. You use a polymer to create a stencil. You don't have a free hanging stencil. You make a polymer, that's your stencil. You selectively remove the material to get the grooves in your Rangoli stencil, and then you shower metal. And that metal goes and touches graphene. And then once the stencil's job is done, you get rid of it completely. And you will end up with the situation that you want, which is connections to graphene. Okay, so this blue polymer is easily removable, and what you get is contacts that you want. So this is just a cartoon, but this is an image of the same device before and after making these electrical connections. These are about a micron small. They can be much smaller as well, but this is a nice example that I like. So how am I doing on time? Okay, I'm quite behind schedule, but I hope to end the pedagogical part later on. If somebody has questions, then I can talk about actual experiments that we also do. So one fun thing that happens is that when you twist these materials, physically you twist them, but it also hybridizes the electronic states in the 2 layers. And the way to think about it is that a real space rotation also translates to a rotation in the momentum space by the same angle. So if I just look at one Dirac cone, this is the lower layer, this is the upper layer, again Dirac cone, but in this scenario, the electrons are not allowed to go back and forth, they're just proximal. But now when I allow electrons to hop back and forth, there is hybridization when these states are degenerate. And that hybridization opens up gap. This is not very different from simple formation of a chemical molecule with 2 atoms. You have orbitals, and when they degenerate, the hybridization, the fact that electrons hop back and forth, opens up gap, and you get a modification of these bands. You get opening of the gaps similar to what you would be a consequence in the chronic penny model. In extreme case, what can happen is at some angles, you can have this band, this part of the band become extremely flat, and that's when the electronic rates of hopping between the two layers is the same as the hopping rates between the Moiré lattice that I showed you earlier. So the Moiré lattice is this new lattice that is formed, which is about 10 nanometers. If those hopping rates of electrons in the lattice and across is the same, you get extreme flatness. And these get bands. You start with something which is dispersing linearly to bands which are very, very flat. So if you like, the Fermi velocity that was here, let's say some 10 to the power 6 meters per second, here it can be substantially reduced by a factor of 100. So these Fermi velocities are now renormalized because of this interaction. Now, this has led to the fact that you can engineer these bands. The amount of flatness of these bands is a function of the twist angle, because the twist angle is controlling the hybridization of the electronic states. People have discovered a lot of exciting properties. Starting with only all carbon systems, people have discovered the flatness of the bands. You can think of the kinetic energy now gets quenched because the Fermi velocity is significantly reduced. Now, if there were electronic interactions, exchange interaction, for example, they automatically get relatively enhanced because now the kinetic energy contribution is reduced. And so people have seen existence of, or rather consequence of electronic correlations like superconductivity and magnetism come because you have now quenched the kinetic energy contribution. So this superconductor is very unusual superconductor because it doesn't involve any other known elemental superconductor. It's just all carbon. Its critical temperature is nothing to brag about. It's just about 2 Kelvin. Some engineering you can get a few Kelvin. But what is interesting is that the TC ratio of this critical temperature and Fermi energy is very close to 1, which is very unusual. In other superconductors that we know, the TC is of the order of a Kelvin and EF is electron volts. So there is orders of magnitude difference, but these superconductors are unusual. These magnets are also unusual in the sense that the magnetism doesn't arise from the spin degree of freedom, because there is no spin-orbit interaction in these systems. It's actually these loops of currents that are flowing around. It's an orbital magnet because loops of current give rise to tiny magnets, and you get these spontaneously time reversal symmetry broken states with non-zero Chern numbers. So this is connection to the question that you asked. These are not just mathematical construction, but you can actually measure, for example, Planck's constant from these experiments to a pretty good accuracy. Not as good as quantum Hall effect, but still, so these ideas are extremely robust and give rise to magnets which are fundamentally new kind of magnets away from the paradigm of magnetism that we know. Yeah. This is in a no, not quite here. It's somewhere else. This is a slightly different system. You have to break some other symmetry by aligning it with hexagonal boron nitride.
What's quite amazing is that it's very close to the phase diagram of cuprate.
Yeah. So that initially there is still a lot of discussion. There is a lot of I would say. It has given some new insights to attack the cuprate problem. I think people disagree on how close it is to the cuprate, but there is a new impetus, let's say. Yeah. Yes. The beauty is in these superconductors you can tune the Fermi energy continuously on demand, which you could not do in cuprates. You had to make new sample every time you had to dope it. So the allure of this system is clear, but difference is also clear. Okay, so overall this system is very rich and fruitful because analogous to what Krishnendu was talking about, quantum simulation using atomic lattices or in atomic potential. You can also make quantum simulators of different states of condensed matter by twisting layers to engineer the Hamiltonian. So essentially every bit of exciting physics can be at least attacked in a unique way by engineering the Hamiltonian. So there's lots of interesting physics I already talked about, which makes this a fun system. We have in my lab focused more on understanding these properties of the topological structure of these bands and not just the correlations, because the correlations are interesting and we work in that area as well, the superconductivity of these flat band superconductors. What we like is the fact that you can start with a band like this, break inversion symmetry, create a moire, and realize some non-zero valley churn numbers. Then you can actually break some symmetry of the system, break time reversal symmetry, and you can get interesting playground for engineering various symmetries. You can break some other spatial symmetry, which is sort of what I will talk about if I still have time left on research, which is if you strain the system anisotropically, you break the C3 rotational symmetry that is native to the honeycomb structure, and you can get a first moment of the Berry curvature, which is sort of like a lumpiness of the Berry curvature distributed in momentum space can actually have physical consequences. So overall, this moire field, it's very young, it's starting 2018, it has led to a very furious activity in different aspects of condensed matter, and we are sort of one of the people kind of hustling in this field to understand interesting physics. So some landmark discoveries are this quantum anomalous Hall, integer quantum anomalous Hall state, and recently there has been really amazing experiments just 2 years back of people have seen fractional quantum anomalous Hall, which is essentially analog of the fractional quantum Hall effect, but now by just using the structure of the moire and the Berry curvature to realize interesting systems at zero magnetic field. Naturally, people are furiously trying to understand what is the nature of these quasi-particles that live in this fractional quantum anomalous Hall state. So what is it that these moire systems do which is different from the material that we already know? So one is important is this length scale. They bring a new length scale which is completely tunable to our disposal, and what it does is it gives you a way to tune the magnitude of the Berry curvature. This is a comparison with God-given 2D lattices, and this is God-given 2D lattices, and this twisted 2D lattices. So they offer a way to sculpt the structure of the Berry curvature and the first moment of the Berry curvature, which is called the Berry curvature dipole, and that's sort of why we are interested in these systems. So I have talked about this, which is largely an introduction, and I hope that conveys the overall excitement. In the next remaining 5 minutes maybe, 5, 6, great. That's enough for me to talk about one of my experimental results because that detail is not that interesting. So we have been looking at, I already talked about bilayer graphene, which has this property that you can tune the gap by applying an electric field. What we have been focusing is twisted bilayer, double bilayer, which is essentially 4 layers of graphene, but taken pairwise. You take bilayer, you cut it, and exactly in the way that I told you, twist it and you stack it back. Now you might say, why are we interested in it? The reason we are interested in it is that bilayer itself, when you apply a perpendicular electric field, opens up a gap and there is Berry curvature in the bands. Now when we stack it and we create a moire, it inherits the Berry curvature and further kind of tweaks it a bit more, and that's why we are interested in that. So the fact that this band structure of this new 4-layer structure is completely tunable is the allure for us. So starting about 2020, there is a lot of work away from twisted graphene on this system. which has been sort of the focus of our attention. So this is sort of one example of our device where we can make lots of electrical connections to a stack of these 4 layers and apply voltages, measure currents to understand the properties. What I'm going to do is I'm going to show what we experimentally measure since I'm an experimentalist. So this is the experimentally measured data from our device. So people may not be used to looking at data like this. So this is essentially measuring resistance of this device at low temperature. So this temperature is about 1.5 Kelvin. What these parameters are, this is N controls the doping, essentially how many charge carriers are there, and D controls the electric field. How do we do this? We have 2 knobs, we have 2 gate voltages. So electrostatically I have one metal underneath and another metal on top. So these 2 gates, I can apply 2 voltages. They don't participate in the flow of electrons, but they electrostatically modify the potential that the electrons are seeing. And that 2 voltages can be mapped to density of electrons and electric field. It's a kind of a rotation in that parameter space. And we measure resistance as a function of these 2 parameters. So this purple violet is low resistance, so it's a semi-metal, and large resistance is this red. Okay. So what do we see experimentally is that there are these bands which are sort of bands of color. This is essentially a huge matrix of data measured as a function of N and D. We visualize it by plotting in color because large data set can be visualized much more easily, but these are all numbers behind. So what's really happening? What's happening is that in this state, when you apply these kind of voltages and when you have 0 electric field, the system looks like this. You have some remote bands and you have these flat bands. The flat bands that I talked about. This is sort of detailed numeric calculation of these, and this is sort of a cartoon, and I'll just show this cartoon because it's essentially the same thing without sort of the complications. And as I apply the different voltages, what I do is I tune the bands, the 2 bands which were overlapping and are flat. By flat I mean their local Fermi velocity is very, very small. I apply perpendicular electric field, I will open up a gap in these flat bands and I get 2 flat bands. If I apply further electric field, I will open up further gap and I see this gap here, which is the gap here I see is the gap in the electronic spectrum, which is the red dashed line, which is where the Fermi energy at charge neutrality. And I can further apply voltages and eventually these flat bands will disappear, they will kind of merge with these remote bands. Yeah. Yeah. Okay.
There is a lot of superconducting regions.
Yeah.
You don't get superconductivity.
Good. Thanks for asking that question. So there is no superconductivity in this variant of Moiré system. Okay. People understand, or I think rather don't fully understand, but guess that it's some symmetry that is the C2T symmetry, which is crucial. That symmetry is distinct between twisted bilayer graphene and twisted double bilayer. So there's no superconductivity here, but there are correlated states here as well. But people see it in bilayer graphene, trilayer graphene, which also has that symmetry. So what we have been focusing on is these flat bands and the Berry curvature that arises from these electronic states. I'll show one experiment and then stop and take questions. So the way we see the evidence of this Berry curvature, which I kind of talked about earlier, is that the Berry curvature is distinct of opposite sign in the 2 valleys, or in the 2 vertex, the kind of around the 2 Dirac points, if you like. And if you apply a charge current, when you apply a charge current, when you apply a battery, you don't have a way to control which electronic states are participating. They will participate in equal number. So you send electrons in this loop, but when they go, because of this Berry curvature, electrons of one valley are getting deflected to one side, and electrons of another valley are getting deflected to other side. This is a direct consequence of the fact that the Berry curvature in the two valleys is opposite in sign. Okay. Now, this is a kind of automatic sorting of electrons of one valley goes to one side and another valley goes to another side. Oops. So when that happens, in this direction you actually have no charge current, but you have a pure current of the valley degree of freedom. Okay. This valley degree of freedom can be measured directly, because down the line you can convert this valley degree of freedom back into a charge degree of freedom, again by an effect called the inverse valley Hall effect, which is this very inverse effect. If you just send a pure valley current, then you will get electrons only get deflected on one side. So if you down the line, if I measure a voltage, that will tell me that I only have a pure valley current. If that voltage is 0, then I have no valley Hall, no pure valley current. And that's exactly what we did experimentally in these flat bands, that allows us to quantify what is the magnitude of the Berry curvature and test the ideas that I kind of described to you. This sort of was the starting point for us. Then we also studied other physics, which is sort of these ideas of Berry curvature dipole and studying transitions in the valley Chern number. Okay. If I want to stop, that this is a good point to stop, and I'm happy to take questions. If there are questions, then I'll tell you about that other experiment, but this is a good point for me to stop. Thank you very much for your kind attention.
Is that the Chern number current, or is that something?
No. So there is nothing. There's no time reversal symmetry has not been broken here. So I have an equal valley current of green and blue, but in opposite directions. Okay. If there was a time reversal symmetry breaking, then there will be unequal quantity of these two valley currents. So Chern number is 0 in this experiment.
Then there is some other charge which characterizes that, or what?
Yeah. So what happens is that you think of a battery. The nice thing and the bad thing is that a battery cannot distinguish between electronic states of one value or another. It will push both, and then the Berry curvature kind of splits them. Now, in the transverse direction, if you like, you have a pure current of a valley degree of freedom, because one valley is going this way and another valley. So you can think of in one direction only one valley current is flowing.
Which is one sense of rotation or something?
Yeah.
Okay.
So then when it goes to this point right here, all the electrons of both the valleys here are going to get deflected in one side, because of that inverse effect of this term. So then the voltage on one side is going to be more than the other side. That's just an inverse valley Hall effect. Again, the role is the Berry curvature.
Sorry, one other thing in the previous. Okay.
Okay, so that was the part of my talk. But the total Chern number is 0. Valley Chern number is non-zero. You can assign a Chern number associated with one valley degree of freedom, so that even though total Chern number is 0, the valley has a net Chern number. Okay. So you can talk about it that way, but the total Chern number is 0.
So the quick thing about the previous one, there was a density, electron density or something in the x-axis that you showed.
Yeah.
This one, and why is that a signed quantity? What does that mean?
Sign.
Yeah.
Okay, thanks. For simplicity, let's go back to the graphene thing, that band structure that I talked about. I have Fermi energy at charge neutrality here in the pristine state. If I apply a particular value of to the gate voltage, so the way the doping works is that if I have this one layer of graphene or whatever structure, and I have a gate, and I apply a voltage to the gate electrode, this material now forms part of my parallel plate capacitor. So as I apply a voltage, I can induce either one sign of charge carriers, okay, or if I flip the direction, I will get the other size of charge carriers. Okay, eventually whatever is mobile is electrons, but we use the electron hole terminology. So when you apply one sign of gate voltage, your Fermi energy moves up. So you're putting more electrons into the system. And that is the N positive. It's just a convention. Why electrons N is positive is just a convention. And when you put the opposite sign of the gate voltage, you move the Fermi energy into the valence band, that you notionally call N negative. That is equivalent to saying you're putting more holes into the system. Okay?
Right.
So I mean, you talked about changing the Fermi energy, also in the earlier bilayer graphene itself, and now here. So I mean, there must be a point at which there's a critical electric field where you sort of cross the gap into one of the bands.
Yeah.
That kind of Lifshitz scenario, if you will. And so the quantum geometric tensor should diverge or show some critical behavior at the
can happen.
Transition from a back.
Yeah, so if there is structure inside your particular Hamiltonian, yes, you can have those kind of transitions.
Yes, so
Lifshitz transitions, for example.
Is there a kind of a manifestation in experiments which can probe the divergence of the geometric tensor?
Yeah, it's hard. Right now it's hard. I mean, a lot of people, including us, we are trying to find ways to access these quantum geometric tensor, particularly the real part of it, because the Berry curvature, as I hopefully have shown you, people have access to it from other experiments, also optics. But
Sigma XY.
yeah, so people are looking at nonlinear transport, which is sort of also what we are doing to access the real part of that tensor. I would say there is still a lot of debate in the community, but these are exciting things that we are working towards.
Yeah, so this tri-layer thing that you mentioned, I think somewhere, so if you make a Moire type thing there with two different rotation angles, does something new happen there, or qualitatively, or?
It is
originally multi-layer thing.
Yeah, so you will get new thing in the sense that the same game can appear one more level. So let me just go back to the image. So at some zeroth level, what happens is that you twist two layers, you get a new length scale, which is the beating pattern. If you put a third layer, which is at a slightly different angle, that will beat with the already new length scale that you have. So it's a kind of an interference of electronic states, wave functions, if you like. So it is also a knob. So people are working on it. We have done work on twisted tri-layer, which also hosts superconductivity.
Yeah, so are there qualitatively different things that happen with the superconductivity or the ferromagnetism that you mentioned with it?
Yeah, so there is a broad theme, which is sort of what I tried to show in the talk today, but there are some specificities of each system which people are still trying to understand. For example, when systems have this larger class of Moire, which is not just 2 layers, 3 layers, 4, 5, can show superconductivity when some symmetry is protected. That is understood. Now, exact details of each twisted layer is somewhat not understood, and there can be some, I would say, it's like you have sambar, which is sambar, but there is a sambar which is spicy, one which is not so spicy, and some variants of it. So that's the difference. So common themes are there, so it's not like a mess of weird results, some common thing which is broader understanding of the field, but there is some finer details which are still people are figuring out.
Right.
Does that answer your question?
Yeah, it does. So one other thing relatedly is that if you have, if you now go from the bilayer thing to trilayer and then, multi-layer, but do it in an ordered way.
Yeah,
then
people are doing it.
Does everything just go away then in the multi-layer limit, or
no, some features persist. So they persist at as sort of effectively boundary modes. So if you have like 10 layers of some material, then somehow the states which are associated on the surface know what has happened down deep inside the layers.
Okay, my question relates to your statement that you can tune some of these parameters. So do you think that this can be used, for instance, in devices to, let's say, detect terahertz radiation and so on?
Yeah.
Has it been done already?
Some people are doing it. We ourselves are doing it not with Moire but with other systems. So you can, these gaps, thanks for asking more. Thank you for that question. It allows me to, as an experimentalist, something that's close to my heart is applications, allows me to emphasize that. So these gaps that I showed, you can think of this material as a tunable semiconductor. These gaps are about 10 MeV. And by suitable engineering, these can be tuned. Beyond the twist angle, I can apply a voltage and I can get the gap to be precisely what I want. So there is indeed that angle to this field as well.
One can make very compact detectors for terahertz.
Yeah.
Thank you.
Final question. So within the landscape of knobs that you have available for tuning, is it known whether there are quantum phase transitions in this system? I mean, the reason I ask is because of this question about the quantum geometric tensor, and the singularities or the divergence of quantum geometric tensor is usually a signal of quantum phase transition. So unless you have accessible quantum phase transitions,
thank you for that question. This is sort of related to my question, but anyway, I'm trying to use it to talk about the part that I did not, about experiment that so in these you can, as you tune the electric field, you can indeed have valley churn transitions, okay, which are so you can think of them as quantum phase transitions if you like, and there are other varieties. This is not done. So across this transition, you do expect these quantum geometric properties to change radically. So in fact, across this transition, we measured experimentally the first moment of the Berry curvature dipole, and it undergoes a transition. Okay, we did not, so that is still the imaginary part of the some component of the imaginary part of the quantum geometric tensor, but it should be in principle possible. This physics is also possible in the fractional quantum anomalous Hall system, where also you can apply just an electric field and go from some fractional quantum anomalous state to another fractional quantum anomalous state, or go from a fractional quantum anomalous Hall state to an integer quantum anomalous Hall state. Yeah, or there's a zoo of physics which I think he knows more about than I do, but yes, it is indeed possible. Now the critical question is what experimental knob to access that structure of the quantum geometry. That's still experimentalists are scratching their heads and collaborating with theorists to figure out. What seems to be the clue is that not the regular transport, but the nonlinear responses of the system can give some inkling of these properties.
Okay, so those who want to leave can leave, but
Just one I just have a small question. Very silly.
No, she has a question. Please.
I don't have a question or a comment.
Yeah.
I just have a suggestion. Your work looks so interesting. I wish you had spent more time on it. I strongly suggest to Ajit that he invite you back to IMSC so we can hear more about your work.
I'm happy to. I enjoy coming here. As I said, the meeting here organized by Bhaskar and Shankar led to the genesis of some of the key ideas that we are doing now. Of course, we have gone deep into it, but the genesis was here. So I always have fond memories. I would love to come. I'm happy to answer questions more over lunch whenever.
Very silly question. Monolayer, this thing will be about, size will be some nanometers, right?
Thickness,
Thickness,
it's less than a nanometer. The
I'm not going
CC
to
bond in plane is about order of an angstrom.
Yeah. So I'm not going to be able to hold it with hand or anything like that.
If you will be able to hold it by a hand, but you will not know whether you're holding it or
Exactly. So how do I arrange this engineering part? That
Okay,
it's an
all
experiment.
right.
I don't know. I'm just curious about this. No. So that's what I'm asking him. So.
I like it.
I don't know how it works.
Yeah, so I think that's also a lot of creativity, and let me just show one image just to, okay, this, I'll use this because this is a nice, so at the outset let me say that for these things I'm useless. Okay, maybe 20 years ago when I was a grad student I was good at it, but now I'm useless. I'm grateful to the students who work because they know how to do it. I can only describe it. Okay, so you should take it with that spirit. So the way it's done is that you use a sticky polymer. So you can think of it as a sticky rubber eraser. Okay, so what we do is literally we cut the graphene under a microscope with a sharp tip. Okay, I may have a video of it. Let me try to see if I can pull it out. We just from the microscope we're looking continuously. You can't do it in the dark, and then you just move because this is only one atom thick. It's very fragile and also strong at the same time. You can scratch it, and the scratching just cuts it into two pieces. Now the aid is your sticky rubber. So the sticky rubber has a polymer like a plastic film which likes to stick to things. So you take that, you heat it to the right temperature, it becomes sticky, and you pick up this boron nitride. Just all the while you're looking at it from the top from the microscope, so you're not in the dark. Okay, so that's why this polymer is transparent. So a microscope is seeing what you're touching, what you're picking up. It picks up, then I go and I sort of bring it down, very precise control over z-axis motion of the sticky polymer. Bring it in contact, touches, peel it off and go up. And oh yeah, I mean I showed you these are real simple optical microscope images of it. Now the physics of why it's visible is also something that you are probably going to ask me. Is it relies on thin film interference. It's basically it's only one atom thick, so it only absorbs 2% of light over a wide range of energy. What it relies on is below this the substrate, which looks purple, is actually a precise thickness of silicon oxide, which is a dielectric. Okay, and underneath it is silicon. Okay, now this thickness is about 285 nanometers thick, and this was a kind of major experimental breakthrough in the not by us, by others, that when you put graphene on it, there is some interference that happens here away from graphene. Okay, but the interference with just one atom thick graphene shifts the spectral content of the reflected light just enough that the difference of this is not zero. Okay, and that's where this thickness, certain thicknesses are important. It involves the dielectric constant of the material because it's an optical path length argument. So once you involve the right kind of dielectric, even the slightest bit of it changes. It's like in a monsoon, I'm sure in Chennai, at the auto stands you will see puddles of water and then you'll see the rainbow colored film. That's interference because as the oil from the autos has leaked onto the water puddles. It's exactly the same physics happening here. It's thin film interference that allows you to see it. So even though these things are super thin, the interference physics allows you to see and real-time manipulate it. Yes, yes. It becomes easier. You can use other tools, but the name of the game is fast throughput. If you just stick something in a microscope and you see it with your eyes, it's done in a fraction of a minute. Whereas you can use a more complicated tool like atomic force microscope or STM or SEM, but that takes 2 hours. So that's faster throughput becomes easier in a simple microscope. Yeah. So it is. Again, I cannot tell you, I'm fairly useless. Yeah. Sorry?
You know that you picked it up? Or you
Yes. I'll see, you can clearly see it. It's a little bit tricky, but because the tricky part, and you're, I think probably getting to this, when the thin layer leaves that precise substrate, you actually cannot see it. When it goes to the sticky polymer, it's actually much harder to see it. But the fact that there is nothing left behind on the purple substrate tells you that you have picked it up. It's a skill. So it requires a lot of, a skill which professors don't have, but the students have.
So when you take a white paper and put one layer of graphene sheet, according to theory, the absorption coefficient is related to fine structure constant.
Exactly.
It's amazing that many things drop out. Finally, fine structure constant.
Yeah.
So if you put 2 of them, it's 2 times the fine structure.
Yeah.
So 2%.
Yes, that is a very beautiful work which show. It's a simple quantum mechanics problem for
Okay, on that note, it's time, Nanda.